All right, guys, thank you all for coming. I know it's confusing getting up here. A lot of people down there waiting to get up here, but we got to start. It is 9 o'clock. We promise to respect your time today. We are going to do a lot of things here today. We're going to start this morning with Brian and the basic storm spotter training. And by the way, for those of you watching online, thank you for watching. We'll start with basic training. After that, I've got some things to say. I'll be speaking about the state of the warning process in the country, where we are, where we've been, the problems we have. I'll talk about last Wednesday. A lot of things to talk about. We'll have a lunch break. We'll come back with the really good meaty part of this, which is the advanced session. Some of you have been trained before, some of you have not. And I like to come back every year. And again, I've been doing this a long time, but I like to hear Brian because every year we learn something. There's typically something new. But before I bring up Brian, let me bring up Megan. She's our weekend meteorologist at
Thanks, guys, for coming. It's good to see you, and I'm glad I could point some of you in the right direction who all looked lost, because I was one of those about 10 minutes before you. So what's going to happen at the end of this, once Brian gives you the whole shebang, there's going to be an email that you're going to see. Skywatchers at ABC 3340. You don't have to write it down right now, but there's going to be a slide. You're going to write it down then, and what you're going to do is you're just going to send me an email. It doesn't have to say anything, but hey, I will take that email that you send it to me from and put it in our new system, so you are an official Skywatcher and you get to be a part of this program called Slack. And what that does is you can report your highs, your lows, your warning or your rainfall totals and pictures and everything like that. It's a great way for us to see what you see, because we are all trapped in one little spot where y'all are all over the entire state. So we have some of our Skywatchers who are already here who are involved in that. I know several of you. So we really appreciate it. And again, it's skywatchers at abc3340.com, and just send me an email and we'll get you plugged in that way. So that's my spiel.
All right, that's good enough. Yeah, and again, Slack is a platform. This is a platform for communication. That's what that is. There's real-time chat. You can put images and video there. There's direct messages. The bottom line is you got a direct pipeline to us, which is kind of nice, and that's closed. It's not open to the public. It's for those that have been trained at these sessions, and we know that if there's a report coming in that way, then it's good because you've been trained. So again, after we're through, we'll get some more information about that. We'll explain how that works. For those of you that do have instruments, and not everybody does, but we'd love having those reports every night. We use them on the television news with high, low, and rain. But on active days, the big days, winter storms, tornadoes, severe storms, hurricanes, things like that, floods, your reports are just crucial, because that will make what we do much better. So without any more talking by me, I got a lot to say. I'm afraid I'm going to get cranked up and cranky and wild today here just a little bit. But Brian's going to do his thing first, and then I'm going to do my thing. So this is Brian Peters, the man that looks like Colonel Sanders.
I keep telling him he needs new material. That's what you think. Everybody doing all right this morning? Actually, you're extremely well qualified. If you can find this place, you're very well qualified. You know your directions, and you can become a storm spotter by knowing how to find this place. So it's always out of the way, but we're happy that you all are here. I always like to start off with poking a little fun. Oh, I don't know. I have no idea. How long have we been doing these things at the BJCC?
About 10 years.
Well, then that picture's at least 10 years old. All right, this is the way that we normally see him, okay? So, but after extensive research, I found a lot of pictures of James doing a variety of things. He's quite wild, actually. When Halloween comes along, he always goes as an iPod, because he's an Apple Mac guy, okay? So,
This is not working, man. You can just tell when a comedian's dying. This is not working.
and then we found some top secret stuff. You know, James has been into a lot of research, primarily with weather, but he's also done some sound research, trying to sense things going on in the atmosphere in a variety of different ways. That's him over there with the two tubes, and there he is again, you know. All of this found in the National Archives, by the way, and there he is. Of course, I love the cigarette over here. Okay. And then he had some secret aspirations to become a space shuttle pilot. But he discovered some terrible flaws with the space program, like bloating. So he could envision himself that way, so he decided maybe he didn't need to go aloft after all. And then more images found at the National Archives. James will be the first to tell you he's been doing television since the Civil War, and we can prove it. There he is in the Civil War back there. He's on the left over there, casually. I love the boots. They're really cool. Yeah, you really were. The hat at the rakish angle of a cad. So anyway. And then, of course, we have Voodoo Country, which if you watch the blog, you're familiar with that. And James sometimes gets into the Yoda pose every once in a while. And then some new material that we just found. He is in collusion with the bread people and the milk people during winter weather events. And this viewer caught this, Megan helping James get the bread, snap up the bread during a winter storm. And then, of course, you mean to tell me the hokey pokey isn't what it's all about? This is philosophical James right there.
Wow. I'm sorry. All the way down here for that.
Okay, let's get to something serious, all right? Megan, can you hand me that bottle of water? I'm gonna go thirsty here before, or dry. Yes. I have a dry mouth here. Okay, we're going to talk about a variety of different things. The main topics include tornado climatology, some characteristics about tornadoes, the storm structure of thunderstorms, and the visual characteristics that you and I can watch for. We'll also touch on storm safety, and I haven't put down here at the bottom, but we're going to end the basic session with videos that will help, I hope, help you visualize and put into motion some of what you're seeing in the still photographs. But before we start, I want to ask a why question. And the why is kind of a two-part question. The first why is, why do we need storm spotters? And there's actually a fairly simple answer to that question, and that's this graphic right here, which was produced by my good friend, the WCM in Norman, Oklahoma, Rick Smith. But radar gives us a lot of information, but not at the ground. It's only in the thunderstorm. The radar actually goes through a series of volume scans, and what that means, and we're going to get into more of this in the advanced session, more on radar, but what that means is that the radar sends out a beam and circulates at half a degree. The revolution, or the dish, is moving at 3 revolutions per minute, so it only takes about 20 seconds to go around once. Then the radar tilts up about 1 degree, so it goes up from a half a degree to 1.5 degrees, and then it does another slice. Then it goes up to 2.5 degrees and does another slice. Why do we want to do that? We want to do that because it gives meteorologists this information about structure of the storm. And you're going to see in a graphic in a few minutes the continuity that meteorologists are looking for, especially when it comes to velocities. And that velocity couplet that shows where a mesocyclone is, not where the tornado is, but it shows where the mesocyclone is. But the problem is, since the radar is above the ground, giving us lots of information, we don't know, even if we see a tremendous couplet up here, we don't know absolutely positively for sure that there's a tornado at the ground. So that's why we need storm spotters, because this is what we refer to sometimes as ground truth. This tells us exactly what's happening at the ground, and we need eyes and ears reporting that. Now, we're not training you to be a storm chaser. We're training you to be spotters, which means you're at a fixed location. You're watching the storms move by you, but you need to know what you're looking at. One of the problems is we do get false reports. Not necessarily false reports that are intended to be malicious. They're false reports due to a lack of knowledge. Every V cloud, every V-shaped, funnel-shaped cloud in the atmosphere is not a tornado or a developing tornado or a funnel cloud. But people have that impression, and so false reports can come in. But as I said, we're not training you to be storm chasers. We're training you to be storm spotters. And why aren't we training you to be storm chasers? Well, that is answered with this picture right here. You may have heard of the wreck a couple, 3 weeks ago with the death of 3 storm chasers. That was a terrible tragedy that had nothing to do with storm chasing. It had to do with lousy driving. When you avoid or when you ignore stop signs traveling at high rates of speed, you can expect to have a wreck. And unfortunately, 3 deaths occurred out of that very tragic event. This event is perhaps even more tragic in a way because they didn't collide with another vehicle. They collided with a tornado. And this happened to be the car that 3 storm chasers were in, a father, son, and a colleague. And actually, the father-son combination, they've been chasing for a long time. The father was actually a very strong proponent of safety. So the question you might ask is, well, how did he get into trouble? Well, very interestingly, we had another storm chaser, Tim Marshall, talk to our National Weather Association chapter just a few weeks ago. And Tim was on the El Reno, Oklahoma tornado also. And he said, as a storm chaser, we usually expect tornadoes to do 3 things. We expect them to broaden, get stronger and get wider, to strengthen, and the wind speeds to go up, and perhaps even change direction. What happened in this case right here, though, is the El Reno, Oklahoma tornado did all 3 things simultaneously. It widened, it strengthened, and it changed direction, all at the same time. The tornado actually moved in an arc, believe it or not, and it was extremely wide. As a matter of fact, I believe it goes in the records now, if not the record widest, it's very close to that, on the order of 2.3 miles at one point, and was definitely what's considered a multiple vortex tornado. When tornadoes get large, and that usually means over about a quarter of a mile, they tend to break down into multiple vortices. And I don't do much on multiple vortices because, to be honest with you, don't know much about them. But we know that they do move, they do break down. All right, the atmosphere is quite a cool place. This is a shot from the space shuttle, and this little blue line that you see right here that kind of gets a little narrower as you get up here to the top, which is to be expected, that actually is our atmosphere. It's roughly about 100,000 feet thick. As a meteorologist, James and I are more concerned with the lower 70,000 feet. We really don't care when you get above 70,000 feet because there's not much going on up there that we care about that affects us down here. The air is getting very thin. But it is that atmosphere that is responsible for allowing life on this planet, but it is also responsible for producing severe weather. So if you take any year in the stats, I don't care if it's 57, 2002, 2014, it doesn't matter what year you take, you're going to see very similar things. Here are the events that we consider to be severe: tornadoes, thunderstorm wind, hail, lightning, flash floods. This column is the number of those events in that year. And as you might expect, thunderstorm winds, we get more severe thunderstorms than we do tornadoes. We get hail, and these two would lump together as severe thunderstorms. Lightning is actually underreported tremendously, but even this year we had a pretty good number. Flash floods, fair number. This column is the number of deaths, and this is why I show this, because in this column you can see that while lightning produced some, flash floods usually produce some, you can see that in this year, 2002, tornadoes, 37, were responsible for 13 deaths, and that's the problem. April 27, 2011 was perhaps an extreme, if you can go that far in extremes, because we had on that day 62 tornadoes. This year we had 37. 62 tornadoes in one day, and set a new record. In addition to that, we had 252 fatalities. And that just is astronomical. But it shows how powerful tornadoes can be. And as a matter of fact, if a little trivia here, if you lined up all the tornadoes that occurred on April 27th, 2011, if you lined them up from beginning to end, and then the next one, the beginning of it to the end of it, and you line them all up, the furthest end would be 1,100 miles from here. That's 1,100 miles of tornado paths. And most of those tornadoes were F2s, F3s, F4s, or EF2s, EF3s, EF4s, and EF5s. So they were all pretty strong. So we put a lot of emphasis on this because we need the reports. This is just a quick example. This is not from the other Wednesday, last Wednesday. This is actually in Arizona. But I want to just illustrate how even hail can be pretty dangerous. You can see how much it's doing to the trees, damage it's doing to the trees. Imagine if your vehicle was out there. It's creating a need for warnings on that pool there. I mean, I wouldn't want to be swimming in that, would you? you could get hurt. And people do die from being hit by hail. What usually happens is the large ones, baseball, softball size, hit somebody in the head and they crack the skull. So it can be very dangerous. So I want to just point that out, that severe thunderstorms are dangerous. And remember, the two criteria for a severe thunderstorm is winds over 58 miles an hour and hail 1 inch in diameter or larger. So those are the two criteria. Lightning is not a criteria for a severe thunderstorm. Okay? Lightning's pretty dangerous, but there are no lightning warnings out there. All right. Before we get to tornadoes, there are a number of different rotations in the atmosphere out there. Dust devils, gustnadoes, waterspouts, tornadoes. And yes, they're all sort of related, but they're all still quite different. We're going to concentrate on this one, but just quickly want to run through what these other ones are. A dust devil starts usually at the ground and works up, because what's happening is the sun is heating the ground is heating up tremendously fast, heating the air next to the ground. That air begins to rise, creating a thermal, and that thermal, for some reason, begins to get some shear, and that causes rotation to begin. And so it's usually in the desert areas, but because you can see the debris, which is basically the dust. Now, the interesting thing about dust devils is that their rotations go up. They don't come down. To be a tornado, you have to come down. They fizzle in clear air. They're not attached to any clouds at all. You can have them on clear days. They're not tornadoes, though. Tornadoes require thunderstorms. They're found mainly in desert areas. But if you want to do a little fun research, you can go on YouTube and search for Hay, Hay, Nado, Nado. And you should be able to find a YouTube video of some children playing on a plow, or not a plow, but a field of hay that's been cut. And what makes the hay nado, which is a dust devil with hay over that hay field, is what makes it visible is the debris, which is the hay that's being blown around. And the kids have a great time running through it because it's very, very weak. It's probably, maybe winds of 20 miles an hour, so it's not anything that powerful. Yes, they can do a little bit of damage, and wind speeds can reach up to about 60 miles an hour, so they can do a little damage. And of course, if you drive through one of those, you're going to get your car sandblasted for free, so you won't have to worry about that. All right, gustnadoes are sort of close to a tornado, but the thing about it is they usually occur on the leading edge of a thunderstorm. It doesn't have to be a thunderstorm. It can be on the leading edge, usually along the gust front. And what happens is something in here causes a little shear, and it works a rotation down to the ground. You can see the debris. There's no apparent circulation in here, but there is. We just can't see it. The same as with this one over here. There is a circulation in there. So gustnadoes do work their way down. But they're not, again, this doesn't necessarily mean that it's a thunderstorm. So some of the characteristics of gustnadoes is the rotation is weak. They are connected to the cloud base, usually along the gust front. They're not linked necessarily to a thunderstorm. It can just be a heavy rain area. They're relatively shallow, and they are created by shear along that gust front. If a gustnado occurs and causes any damage, it's more likely going to go in the record books as a tornado, because we don't make that kind of distinction. Now, waterspouts are tornadoes, but they're over water. But they are a little bit different from what I consider to be the classic tornado, in that you don't have to have a thunderstorm. It can just be a towering cumulus cloud. Those puffy white clouds we saw on Thursday? Those, when they tower up over the Gulf area or along the Atlantic, they can produce some rain. They don't produce necessarily any thunder or any lightning. And you can get a waterspout out of those. The waterspouts do begin within the towering cumulus or the thunderstorm, and they do work their way down. What's interesting on this one, and this is a great example here, is you can actually see the air flowing in. You can actually kind of follow the air as it rotates into the circulation of the waterspout, and then then it rises up, because this is a rising column in the middle of this. You can see that on this one. The air is coming in here, coming all the way around and into. Not quite as clear as that one. This one, we're at ground level, so it's very hard to see, but it's actually creating a bit of a debris cloud, which is just water, moisture. Now the thing is, if a waterspout comes ashore, it does become a tornado. So they come out of towering cumulus. Again, they often have no lightning or thunder. they can move ashore, and when they do, they become weak tornadoes. One of the reasons why Mobile and Baldwin counties have pretty large tornado counts is that they have the Mobile Bay and the Gulf right there, so basically whenever there's a water spout and it does come ashore, it becomes a weak tornado and can do some damage. There's also a YouTube video out there, I've forgotten about this one, but I think it was taken in the vicinity of Pensacola, where a guy is boating and he tries to chase a water spout. I don't advise that because I think it can capsize you, and that wouldn't be good. But that brings us to tornadoes. And we're going to concentrate on classic tornadoes. So tornado is defined as a violently rotating column of air in contact with the ground. It's not magical or mystical like the Wizard of Oz. It's just air, what we breathe to stay alive. But it's air that's rotating at speeds that vary from as little as about 60 miles an hour to wind speeds that approach 300. We really don't know what the maximum wind speed is because any wind equipment that has ever been hit by a tornado has been destroyed. So, we get wind speeds going up and then the instrumentation blows away. So it's, when you take the cups off the anemometer, it can't measure anything. Now, we have got measurements indirectly, excuse me, from having a Doppler on wheels. That's a DOW, as opposed to the Twister movie of the COW, okay? That's a joke. Okay. The Doppler on wheels was started at the University of Oklahoma, and the purpose of that was to put the radar on a mobile platform to where they could drive it to a supercell thunderstorm, set up, and get close at measurements. Using that, in Spencer, South Dakota, they measured wind speeds around 284 miles an hour, and near Moore, Oklahoma, they measured wind speeds of 315 miles an hour. Now, the problem is that they're measuring wind speeds around 700 to 900 feet. Why is that a problem? Well, what we know about the atmosphere is that the closer you get to the ground, the thicker, the more viscous the atmosphere is. So the wind speed of 300 miles an hour, or let's say 315 at 900 feet, will not be 315 at the ground. It will be reduced, and there's actually a formula. I don't know what it is, but there's a formula for that. So you could see wind speeds probably in the range of around 295 or so. So that means 300 is not completely out of the question. Now, that's a far cry from when I first started in weather, which was over 50 years ago, and people used to think that tornadoes had wind speeds of 600 to 700 miles an hour. And we've come a long way from that. What makes the tornado visible is a combination of factors, two primarily. One is cloud, water, condensation. That helps to make the funnel visible in all of these cases here. In addition to that, and this one is the most graphic image right here, is we get debris from the ground. Anything that the tornado is destroying can become part of the debris cloud. There's also another interesting video, and I'm not quite sure how you find it on YouTube. It was taken in Tennessee in April of '98. I believe it was either the week before or the week after. I think it was the week after April 8th. But a fellow was driving along US 64, and 64 runs from Memphis to Chattanooga, pretty much a straight line. And he's driving along, moving eastbound, and he's filming out the driver's window, and there's a tornado, and it's also moving eastbound. The tornado is probably about like this. It's kind of gray. And then all of a sudden, the tornado just miraculously appears to be, it turns brown. Well, then it kind of settles back down to gray, and then boom, it turns brown again. Well, it does this several times, and the guy was really curious when he was watching his video, so he went back out there and started looking at the damage path with a little more detail, and he found that every time it turned brown, the tornado destroyed a hay barn. So the hay was turning the tornado brown because all that debris was getting, brought up into the tornado funnel, and so it turned brown because it had all these hay bales and hay that was just up in it. The tornado is part of and develops out of the thunderstorm, which means the tornado will move with the thunderstorm. So if I'm a thunderstorm and I'm moving this way across the stage and I produce a tornado, it's not going to move that way or that way. It's going to move in the direction the parent, the thunderstorm, am moving. Now, there is one exception, and it's been documented out in the western states, the Central Plains states. I hate to use the term tornado alley, but that area out there. It's when a thunderstorm produces a tornado and the thunderstorm itself is nearly stationary. What happens is the mesocyclone that is responsible for producing the tornado is strong enough that it can actually cause a tornado to go in a circle. Because you've got the mesocyclone, which is a broader scale rotation on the order of 6 to 12, 14 miles, something like that. So you've got this big rotation, and then it comes down to the smaller rotation of the tornado, but the tornado itself gets kind of caught up and rotates around that mesocyclone. Now, that only happens when thunderstorms are stationary or nearly stationary. We just don't see that in the southeastern U.S. Thanks to the upper air flow over our region of the country, most thunderstorms are going to be moving at anywhere from 15 to as high as 70 miles an hour, with the average forward speed being about 35 to 50. So we just don't see that situation very often. So some of the characteristics here, the tornadoes come out of thunderstorms and they move with the thunderstorm that produces them. The main direction of travel is from southwest to northeast, and that's in the spring months and that's in the fall months. Now, other times of the year, there can be some different directions, because thunderstorms in the summertime can move from east to west if the airflow is that way aloft, so we can get that flow. And if a thunderstorm is moving from east to west and it produces a tornado, even though a weak one in the summertime, it will be moving from east to west. Now, in the late spring, around the middle of May towards the latter part of May into June, sometimes as far as the middle of July, we sometimes get under a persistent northwesterly flow. And what happens then is thunderstorms that occur will be moving from northwest to southeast. If those thunderstorms produce a tornado, it's not going to move from southwest to northeast. It's going to move from northwest to southeast, the same direction that the thunderstorm is moving. Forward speeds can be anywhere from 0 to 70. As I mentioned, 35 to about 50 is average. This 70, by the way, was documented in Mississippi, in the Jackson area in central Mississippi. And wind speeds in tornadoes are going to vary from 60 to about 300 miles an hour. Again, we don't know the max, but 300 seems to be about right. If you look at tornado deaths in the United States since 1950, and all of these statistics we use are based on values since 1950, because that's when good numbers began to be collected and better collection was put into place. What's interesting here is, and the Chamber of Commerce would be raising their hand here, not wanting me to say this, but Alabama unfortunately leads the U.S. in the number of tornado deaths. And that's all because of April 27, 2011. On April 26, 2011, we were actually in third place. But when we kill 252, or the tornadoes killed 252 people in one day, we jumped way ahead of Texas, who was in first place and had been in first place for a long time, like 25 years. But what's interesting, and I mentioned just a moment ago, I don't like the term Tornado Alley. I don't like that term because I think that's a term that we use to try to make tornadoes be, or make us feel more comfortable, because that means tornadoes are someplace else. Tornadoes, yeah, we get a few in the southeast, but they're in Tornado Alley. That's out in the Central Plains. Well, that's not true. Interestingly here, if you look at southeastern U.S. states, and this is just based on deaths, here's a southeastern state: Alabama, Mississippi, Arkansas, Tennessee, Georgia, Florida, Louisiana. So, out of the top 15, 7 of the states in the top 15, almost half, are in the southeastern United States. It's one of the reasons why I hate the term Tornado Alley, okay? We have an overabundance of tornadoes that kill people in the southeastern U.S., and I think that's an issue. Part of the reason I think that they're using this Project Vortex 2 Southeast to try to study tornadoes in our part of the country. If you look at Alabama tornadoes by year, first of all, I do not believe that in 1950 we only had 2 tornadoes, okay? Does anybody happen to know what the population of Alabama was in 1950? I keep forgetting to look this up until I'm giving the talk, and then I think, I need to look that up. My guess is the population was somewhere between 1 and 1.5 million, would be my guess, back in 1950. The population now is somewhere around 5 million. Well, what that means is it's very difficult for a tornado to occur now and not affect somebody's property. Yeah, it can still happen. I mean, there's still some pretty big areas of the Talladega National Forest, but it's pretty rare that that happens, and even rangers know about some of that damage out there. So while it looks here like if you kind of draw a line, it looks like tornadoes are actually increasing. Oh my God, it's got to be global warming. No, it doesn't. What? Does anybody know what happened here in the early 90s? Radar expanded. And what capability was that? Doppler radar, absolutely. So what happened here in the very late 80s and early 90s for Alabama, is that we began deploying, the Weather Service, began deploying Doppler radars. Well, what did that mean? What that meant is, watching the radar, I would see a mesocyclone, the indication of the potential for a tornado. Doesn't mean a tornado's there, just the potential. We would see rotations. We would issue tornado warnings, and we'd get back no reports. A good example, and I'm not picking on, anybody here from Coosa County? No, okay, good. Well, I'm not picking on Coosa County. They happen to be one, if not the smallest population in the state of Alabama. There's 67 counties in the state. So they're a very low population. Well, we had, on this one day, we had this tremendous velocity couplet that moved across Coosa County from southwest to northeast. And it was like, okay, why didn't we get any reports of a tornado? We issued a tornado warning. So the next day, my colleague and I, we plotted the velocity couplet, and we got in a car, plotted it on a map, got in a car, and drove out to Coosa County. And I said, well, are we getting close to this? We're driving north. And he said, yeah, we're getting close. The road's going to kind of turn to the right and then turn back to the left, kind of lazy S, and we should be pretty much close to the track. Well, as we did the right turn, there wasn't anything. But as we come back to the left, all of a sudden, trees are down on both sides of the highway. As a matter of fact, the highway's been completely blocked. Somebody has been in there and taken a chainsaw and trimmed all the trees that fell across the highway. So somebody knew that that had happened, but the report never got to the Weather Service. So all of a sudden here, thanks to Doppler radar, we have a report that we never had before. Yes, sir?
Yeah, do you remember we had a tornado in 2012?
Yes, yes.
That destroyed down Tuscaloosa?
Yes, yes. So anyway, yes, the number of tornadoes is not increasing like the graph would suggest. What's happening here is our population continues to go up. We have the advent of new technology, more techniques to find reports, the population becoming broader and filling in much of the land. So actually, if you look at the number of tornadoes from 50 to 2016, the average is about 22. But if you cut it off here and take an average of these years since about 1990 or so, the average turns out to be about 37. And I think that average is probably a much better number because back in these years, the truth is tornadoes were being underreported. Now, tornadoes occur in all months. That's kind of bad news for us as storm spotters. So we always have to be on our guard because we can have tornadoes in every month of the year. What's interesting, though, is that in our peak season, March, April, May, the one we're right in the middle of right now, and in our secondary season, which generally is November, but can begin on the last week of October and can extend over into the first couple of weeks of December, these secondary and peak seasons, those are the seasons when we have the most violent tornadoes. And I'm talking EF3s, 4s, and 5s. The winter months, most of the summer and early fall months, the tornadoes tend to be weaker. In the summertime, part of the reason for that is that summertime tornadoes and summertime thunderstorms are just not usually that strong. We do get a few violent tornadoes in the winter months because sometimes, December is a good example here. You may remember the December 16th, 2000 tornado in Tuscaloosa. Yeah, what was the high that day in Birmingham and Tuscaloosa? Do you remember? It was lower 70s as I recall. And the thing is, when you have that warm in December and the atmosphere above is very, very cold, you end up with very strong temperature gradient changes from the ground up, so you can develop very, very strong updrafts, and that's one of the reasons why the secondary season goes over into early December. The tornadoes that occur in this area, especially summer, are very much afternoon showers and thunderstorms. Occasionally, these in September and October are also weak, but they are associated with tropical weather systems because as they come ashore, they can produce numerous tornadoes, and that's what usually counts for this number in September and October being so high. Well, just like time of year, the time of day, we have peak hours roughly from about 11 a.m. to about 8 p.m. One of the reasons for that, not the only reason, we have a lot of reasons for thunderstorms to develop in the atmosphere, but one of the things that helps thunderstorms is to have the sun's heat energy. So what happens here at 7 o'clock in the morning, the sun rises, begins to heat the atmosphere. As it contributes heat to the atmosphere, the thunderstorms begin to increase in number, and as they increase in number, they increase in strength, and therefore the number of tornadoes goes up. When you get here to about 11 a.m., the number of tornadoes continues to climb as the atmosphere is warmed by the sun, and then around 5, 6 o'clock or so, the sun begins to get low on the horizon, and we begin to lose some of that sun's energy, some of the heat that it's putting into the atmosphere. The number of tornadoes drops off, as does the strength of thunderstorms. Now, we do get a smattering of violent tornadoes in these months that are blue. Most of the violent tornadoes, though, a large majority of them, occur in the peak hours. But once again, just like time of year, we have to stay vigilant. We classify tornadoes in basically 3 groups: weak, strong, and violent. I used to think that weather was not a terribly political, controversial subject until I got into the business of identifying straight-line wind events and tornadoes, and had one instance where I spoke to a homeowner and I said something about that it was a weak tornado, and the guy was insulted. You know, it's like his house couldn't be destroyed by a weak tornado. It's like, well, it was, but I've learned not to use that, just say tornado. And then the other one was in Mountain Brook. A lot of Mountain Brook residents got very upset with me after I classified an event that was a straight-line wind event. I classified it as a straight-line wind event, and they were very upset because they thought it needed to be a tornado because, and they had a good reason, they thought that their insurance wouldn't cover them if it wasn't a tornado. But I've found out that insurance companies cover you for wind. It doesn't have to be rotating air. It's just air that's moving. So we classify tornadoes in these 3 groups. And what I'd like to do now is give you characteristics of each of these 3 groups. And we're going to show 3 slides. Here's the first one. And the outline here is that you have a picture. Now, this is a picture of one sample. Okay, this is not every tornado in the world that's an EF0 or EF1 is going to look like this. It's just one sample. And then here are some characteristics. The good news here for weak tornadoes is that about 3/4 of all tornadoes that occur are going to be in the weak category. So if we have a tornado, if you see a tornado, there's a pretty good odds that it's going to be a weak tornado. They cause less than 5% of all tornado deaths. So that's also good news. They don't usually kill people. Can do some property damage, but they don't usually kill people. Now some bad news. Lifetimes are fairly short. Why is that bad news? Well, that's bad news for you and I as storm spotters because it means it's short-lived. So when we see it, figure out that it's a tornado, get our phones out, call in, or do something on the Slack chat and get a report in. By the time we do that, the tornado could be over. So it's impossible then to get out a warning and warn anybody for that particular tornado. Just like lifetimes being short, path lengths can also be short. And those are both kind of bad news for us because what we really like is to get a report and then the tornado stays on the ground for another 20 minutes so the warnings can be out and protect, let people know ahead of time. Now, these are general numbers. Here's a good example right here of a path length generally on the order of a few feet to 3 miles. But I surveyed a tornado in Marshall County. It was an EF0 tornado, but it was on the ground for 9 miles. Hit a number of structures, but did very little damage to those structures, down some trees, but it was on the ground for 9 miles. So we can get rarities that exceed these values. On the Fujita scale or the enhanced Fujita scale, these are EF0s and EF1s, and I'll make a note here that these are the hardest to forecast. And why is that? It's because the conditions in the atmosphere that meteorologists are looking for are not going to be that extreme. They're going to be marginal conditions. You know, you're going to have sort of enough moisture. You're going to have sort of enough temperature gradient change with height that's going to be close to enough to produce some updrafts, but maybe not exceptionally strong ones. So it's very difficult to get out watches and warnings ahead of time for these. You're not going to get advanced forecasts 6 or 7 days in advance like you did on April 27th of 2011 with weak events. Maybe you're going to get noticed a day or two, but these are the most difficult, and if we miss any, they're going to be in this category of storm. When you move up the scale to strong, the number of the tornadoes that are in this category drops off significantly. So that's good news. The bad news is, though, that the number of tornado deaths goes up substantially. 30% of all tornado deaths are in strong. That's the EF2 and EF3 category. Lifetimes can be over 20 minutes. Path lengths can be over 15 miles. Does that mean if you have a tornado on the ground for 3 miles, it can't be strong? No, it doesn't mean that. It just means that you're likely to see longer lifetimes, longer path lengths with strong tornadoes. Wind speeds of 110 to 205 miles an hour, and on the enhanced Fujita scale, these are EF2s and EF3s. Forecasting of these events is much easier because the atmospheric conditions that will produce thunderstorms capable of producing strong tornadoes are going to be more evident. They're going to be more identifiable by meteorologists, and we'll talk about some of the things we look for in just a minute. When you get to the top of the scale, and by the way, this is the March 94 Piedmont tornado. This was an EF4. The violent tornadoes account for only 2% of all tornadoes. That's pretty good news until you look at the fact that in the United States, we will document 1,200 tornadoes in an average year. At 1,200 tornadoes, you do 2%, that's still about 25. So that's a lot of tornadoes to be in the violent category. 70% of all tornado deaths come out of the violent storms. And April 27, 2011 was a clear example of that. It was mostly the EF3s and EF4s that produced the fatalities. They can last upwards of an hour or longer. Their path lengths can be over 50 miles. There was a period of time when I would have told you standing up here that tornadoes didn't last usually more than about 75 or 80 miles. We're finding that that's actually not true. Several tornadoes now have been documented over the last 8 to 10 years. One of the most spectacular ones was in Arkansas, documented to be on the ground doing damage for 123 continuous miles. Okay? Now, intensity changes, yes, but there were no gaps in the damage anywhere along that storm. Wind speeds are going to be over 200 miles an hour, and on the enhanced Fujita scale, these are EF4s and EF5s, and forecasts are usually going to be pretty good on events that produce this kind of event. Just a quick pie chart. These two events right here responsible for only about 5% of all deaths, but notice that these two, which are the EF4 and EF5, only 2% of all tornadoes in this category, and yet they account for 70% of all tornado fatalities. Just another way to look at it. So, all right, so let's talk thunderstorms here. Thunderstorm ingredients that we're looking for, we need moisture, instability, and some form of lift. All right, let's take these one at a time. Moisture, we got to have enough. Preferably moisture in the lower and mid levels. That is, we want moisture to be there present from the ground up to about 14, 16, 18,000 feet, something like that. There's no magic number where it ends up there. And we have to have enough, not too little and not too much. Anybody here ever baked a cake? I've baked a cake. I get in the kitchen once in a while. Always scares the heck out of my wife when I do that. But, you know, and I will do things like, well, if I'm going to bake something today, and then I'll say, why do we have to put a pinch of baking soda in this? I don't even want to get it out of the counter. I mean, it's so much work. A pinch, it can't mean anything. So I do it without the pinch. And guess what? My cake is horrible because somehow or other there was something missing. There was that pinch of baking soda, okay? So the ingredients have to be right, and the same is true in the atmosphere. We've got to have the ingredients to be right, and each ingredient has to be to the right proportion. If it's too much or too little, there's been days when we've had updraft strengths that were too strong. Hard to believe that you can actually have updraft strengths too strong, but you can. Moisture, instability. Instability is the ability for air to accelerate upward. And we usually measure that by a rate of change of temperature with height. And you know, in the winter, it's very cold at the ground, but it's very cold aloft, so you don't have as big a temperature change. In the spring and fall, we tend to get these wider swings where you have cold days, but then you have some very warm days. And on those warm days, the upper part of the atmosphere is still pretty cold, just like the cold days. So you get a big change between the ground and aloft. So we identify this rate of change of temperature with height. And then on a source of lift, lift is the agent that gets this moist, unstable air moving upward. You've got to have something to get this air moving. Well, one of the things that we look for is afternoon heating. I mean, after the sun's heating helps a lot. And you may hear, and if you read any of the discussions especially, you may hear James or I or Bill Murray talking about things like, well, we're going to have a lot of clouds, so we're just not going to get a lot of heating near the ground. Well, the heating is being reduced by the cloud cover, which is helping to reflect some of that heat back into the upper part of the atmosphere and not get into the lower part of the atmosphere. Another thing we're looking for is an approaching cold front. Why is that? Well, as cold air approaches, the leading edge of which is called a cold front, as cold air approaches, warm air moves over the cold air. So you get warm air rising over that cold front that's approaching. And then another thing is often an upper level low pressure system, and we especially want that to be just to our west, somewhere over Oklahoma, north central, northeast Texas, somewhere in that vicinity, because that puts the southeastern U.S. in the right location with what we call upper level divergence, which helps to increase the strength of updrafts. So when you get all of these things all coming together, you can basically produce some pretty strong tornadoes and pretty strong thunderstorms, which can then produce strong tornadoes. Now, how do we know what's going on in the atmosphere? Well, the Weather Service at 92 different sites across the country, including the Shelby County Airport, launches something called a weather balloon. Now, the weather balloon gets all the credit, but it's actually the radiosonde down here that does all the work. On board the radiosonde, which is actually a box that's even smaller than this now, as they continue to miniaturize things, but on board that are sensors for measuring pressure, temperature, and humidity. And then by following this signal, by tracking it, we can get information on how the wind speed and wind direction are changing with height. So that gives us basically a three-dimensional picture of what's happening in the atmosphere. Now, I'm not going to try to turn you into junior meteorologists here in just a couple of hours, but we get a plot that looks something like this. We call this a sounding. The red line is the temperature trace, and the green dotted or dashed line here is the dew point. When the dew point and the temperature are close together, you basically have high humidity. You have a lot of moisture. When they're far apart, you have dry air. So in this example here, we have moisture here, and 700 millibars is about 10,000 feet, roughly. So in this case, a little above, maybe around 11,000, 12,000 feet, we have a good deal of moisture in the lower part of the atmosphere. Oh, what did we just say a moment ago about moisture? Preferably in the lower part of the atmosphere. So we've got it. We also have dry air aloft, and that is helpful because as the air parcels begin to rise, they can explosively develop as they get up into the drier air aloft. Here's another example, but it's backwards. In this case, the dry air is down low. Temperatures here, dew points here, the two are far apart, so it's very dry near the ground, but aloft at this level, which is about 600 millibars, roughly about 16,000 feet or so, it gets very moist and stays moist all the way up. I can tell you right now that at this level right here, there's a cloud deck, okay? So this is not a thunderstorm sounding. All right, now I'm going to go back one here because I want to try to illustrate something. We're going to talk about how an updraft and a downdraft occur. And the warm, moist air is coming into the updraft. And this is feeding moisture and energy into the thunderstorm. The downdraft is taking the cool, wet air and taking it out of the thunderstorm. So I'm sorry. I have a new clicker, by the way, and I'm still getting used to it. All right, and let's go back one more here. All right, let's imagine that down here, I just kicked the bucket. No, kicked the bottle. Down here below, we have a little box of air. So imagine a little box of air. And the sun rises, begins to heat the ground. Some of that heat goes into the air right above the ground, and our little box gets kind of warm. That means the molecules in that box are moving pretty fast, okay? So the box is warm, and it's warmer than the air around it. So what happens? It has to rise. Now, as the box begins to go up, it cools because it's exchanging heat with the atmosphere. So as the box, it's warm, and warmer than the air around it. But as it goes up, it cools. But as long as it stays warmer than the air at that altitude where it is, it will continue to rise. So in this example here, if we get a little box and we get rising air and it begins to rise and it stays to the right of our red line, it means it's warmer than the atmosphere, because this is the temperature of the atmosphere. So the air will continue to rise. Our little box will continue to rise. Now, something magic happens right here, and that is all of a sudden it crosses to the wrong side. It is now colder than the air around it. So what happens? It stops. It can't go up. This is a temperature inversion. That is, the temperature increases with height. Because right here the temperature is 0, but right there it's about -3 or -4. Okay? So our little box, when it crosses this line, all of a sudden it's colder than the environment, so it stops. It cannot rise. This inversion at an altitude like this is often referred to as the cap, because it's going to stop any updrafts from developing any further. And if they can't develop any further, you're not going to get strong thunderstorms. Now, imagine that this isn't here and that the red line goes something like this. What happens is our box begins to rise and it stays warmer than the atmosphere all the way up. You have a lot of energy to develop into updrafts. And it is the two elements, the updraft and the downdraft, that compose a supercell thunderstorm. Now, in the updraft area, you have it feeding warm, moist air into the updraft. As condensation occurs, so our little box is rising here, it continues to stay warmer than the air around it, but it gets cooler, and at some point in the atmosphere, it reaches 100% saturation. So that means that any moisture in that box is going to condense out. Well, condensation is an important process to all of this. When condensation occurs, the moisture condenses out, we begin to see clouds. But it's also an important process because condensation releases heat into the atmosphere. Now, we're not talking about enough heat that we could put our hands on the side of our box and burn ourselves, okay? But we are talking about enough heat to help that box to stay warmer than the air around it. So it continues to rise. As it does, as it rises, more and more condensation occurs. So the water droplets are small to start with as condensation occurs, but they begin to bounce together. And what will happen is two little condensation water droplets will bounce together and touch and stick. And suddenly now we have a water droplet that's twice as big as the other droplets. And then another droplet will touch that one, and now we have 3 droplets that are together, and they're bigger than the other ones. As they get up here into the top part, they become enough heavy drops that they can overcome the upward moving air, and they begin to fall. As water droplets fall, the opposite of condensation occurs. Evaporation begins to occur as water droplets fall. Evaporation is a cooling process. And everybody in this room that's ever taken a shower has experienced that process. You know, when you turn the water off and you reach for the towel and your body is wet and you get that little chill. Well, that's evaporation. That's evaporation going on. Your body is trying to get rid of that moisture, and so it cools your skin. So that cooling process now develops. The cooler air is more dense and heavier, so it falls. And now we have a nice machine going on here, the warm, moist air, the food supply to the thunderstorm, and the downdraft taking out the cold, wet air that it no longer needs. Now, I really need to take this next slide and divide it into 2 parts. Just ignore this part over here, okay? I'll stand in front of this part, okay? We're going to talk about this part. All right, now this is a summer thunderstorm example. In the summer, the wind down low is not very strong. As you go up, it's still not very strong. As you go up even higher, it's still not very strong. And you can see, even when you get up here, it's only just a little bit stronger. So what happens is the updraft begins to develop, condensation occurs, releasing heat. The updraft continues to develop, the yellow arrow here, okay? But what happens is bigger drops begin to form up in this part, and then they begin to fall. Well, where do they fall? They fall right through the updraft. Well, that can't be good. You're right, it isn't good, because what happens is this cool, wet air that's falling is cutting off the warm, moist air, feeding the food supply into the thunderstorm. So what's going to happen here is this thunderstorm's going to die. And you know, you've seen examples of that. You know, you've been out in the afternoon at a park somewhere, and around 2 o'clock you hear a little thunder, and you look off to the west, and there's a little shower, and then 3 o'clock you look over to the west, and the shower's gone. Well, that's because it's gone through this process. Now, forget this side. I'll stand over here to block this side. Now we're going to look at this side. This is springtime. What happens in the springtime is that the air speed is pretty good at the ground, but as you go up, you notice it gets bigger. And as you go up higher, it gets bigger. And as you go up higher, it gets bigger, bigger, bigger. So when our updraft develops down low, it doesn't build up this way. It can't, because the air is moving faster and faster, so it tilts over the updraft. And when that happens, these big droplets occur up here near the top of the updraft, but when they fall, they don't fall through the updraft. They fall completely separate from the updraft, creating a downdraft that is completely separate and removed from the updraft. And because of this, we now have a very efficient machine that's bringing warm, moist air, the food supply, into the thunderstorm, and the downdraft evacuating out the cool, wet air. So we can create then, when you get this kind of circumstance right here, you can then create a supercell thunderstorm. The Piedmont tornado of March of '94 actually began, the thunderstorm that produced that tornado actually began in east central Mississippi and moved across all of Alabama, all of Georgia, all of South Carolina, and eventually died nearly 12 hours later in North Carolina. One thunderstorm. And in its lifetime, that supercell thunderstorm produced 5 killer tornadoes. Now, if you want another really trivial fact about all of that, is that it caused deaths in every Cherokee County that it crossed. Okay? Another trivia fact. All right. So let's look at what happens when you take an updraft and you get an updraft developing and it's tilted over, and now you also begin to rotate it. What happens? You now create what's called a mesocyclone. And this is what meteorologists look for on radar, is the mesocyclone. But because I have a mesocyclone, it doesn't mean I know that we have a tornado. So we're going to look at storm structure and identify things that you and I can see and physically identify, and talk about the visual characteristics, and then I'll show some. Now, a few weeks ago, when we were talking about doing this again through 3340, I'm always looking for new graphics, because some of my graphics are pretty old, especially the ones of James Spann. But anyway, I'm always looking for new graphics, and I ran across one, and I thought, oh man, this graphic is perfect. I can use this in storm spotter training, so I decided to throw it in. And after I looked at it for a little while, I said, you know what? I don't think I better do that. Because yes, this has got everything, but it's got too much. So I reverted back to this one, okay? There's two things that are very, very important. The first thing that's very important is knowing what direction you're looking. So we're looking into the middle of the picture here, and that is west. That means that north is over here, south is over there, and what direction's behind us? East. Yes, you guys are getting it. Okay. Now listen, I don't want to make this sound too kindergartenish. Okay. direction is extremely important. It is very important. But I do understand that different people have different ways of handling direction. My wife, bless her heart, I can say anything bad about her I want because I just said bless her heart. My wife, who has been with me for, or I've been with her for 48 years, she has no sense of direction. And she will admit it. She does not. I go someplace and 2 years later I can go back to that same spot and probably find my way around without too much trouble. So I have a pretty good sense of direction. But sense of direction is very, very important. So if you don't have a compass on your car or your vehicle or as you're driving around, try to begin to become a little more aware of what directions you're looking. So we're looking in the middle of the picture. Now, the other thing that's important is where you are relative to the supercell thunderstorm. Now, we're going to start being a long way away. So we're a long way away. How long is a long way away? Well, it could be 15, 20, 25, 40 miles. It could be a long way, okay? Supercells are visible in Alabama from as much as 80 miles. But you're not going to see much. You're only going to see the top when you're that far away. Even 30 or 40 miles, you may not be able to see anything but the top. So when we're a long way away, there's three things we can probably see. We may see an anvil. The anvil is the ice crystal clouds at the top of the supercell. They're ice crystal clouds because it's very cold up here. You may see mammatus clouds underneath the anvil. They look like little pouches. I'll show a picture, a real-life picture of one here in just a minute. And then you may be able to see the main storm towers. The main storm towers represent where the updraft is occurring. And notice that I'm tilting from the rain-free base, I'm tilting up because it's encountering faster and faster and faster moving air. So the main storm towers are tilted over. And those may be visible generally at a relatively good distance, but when you get really close, you're not going to see the main storm towers or the mammatus or the anvil, okay? As you get closer, and especially on the order of 3 to 5 miles, depending on terrain, trees, moisture, and a bunch of things like that, you may begin to see the flanking line and the rain-free base. Now, there's no rain falling here because the air motion is into and up into the main storm towers. So that's the main airflow. So the air is moving into and rising up in the updraft, and it's doing that at all elevations, not just at the ground. It's not like just a solid pipeline. It's a pipeline, all right, but the air is coming in here, it's coming in here, it's coming in up here. It's coming in at all altitudes, okay? And condensation is occurring. More moisture is being condensed. More heat's being released, building up the main storm towers. To the southwest of the rain-free base, you may have little towers like these that are actually referred to as the flanking line towers. These are new updrafts that are just getting started. They're baby updrafts, and they're moving into and helping to reinforce the main storm towers. Underneath the rain-free base, and now we're pretty close now, we're on the order of a mile or 2 or 3. Underneath the rain-free base, you may see an isolated lowering that's referred to as the wall cloud. Sometimes there may be a tail, or what's referred to as the beaver's tail. I'll point out several in some of the pictures ahead. But this is not a feature you need to really worry about, but I will, when we show one, I will explain what's happening there. To the north, remember we're looking west, so to the north and northeast of the rain-free base and the main updraft is where we have the downdraft. This is where the heavy precipitation is falling. Between the downdraft and the updraft is where the hail is falling. So if you find yourself in hail, sizable hail, then you're near the most dangerous part of the thunderstorm because you're near the part where tornado formation is most likely to occur, which is out of the rain-free base and out of the wall cloud. Now, let me state something here to be very clear. Every tornado will not have a wall cloud. Every wall cloud will not produce a tornado. Okay? It's a clue. This is kind of like being an environmental detective because you have to put together the clues you're being given by nature. And nature doesn't always give you all the clues that you'd like to have. For example, I'll show you a picture in a moment of the Cordova, Alabama tornado on April 27th. It had no wall cloud that I could tell at the time that I saw it. All right, let's slice through this diagram. Let's slice through right here, as if we've gone on top of the thunderstorm and we're looking down, or the way radar would slice through it. So it looks like this. Before, we were over here looking west at the rain-free base. This is where the lowered rain-free cloud base is right here. In the northeast quadrant of the thunderstorm is where the downdraft is occurring. This is where the heavy rain is occurring. The southwest quadrant is where the rain-free cloud base is, and this is where the tornado is most likely to occur. Between the downdraft and the base of the updraft is where the hail is likely to fall. So you can see, if you're in hail, you are near the most dangerous part of the storm where tornadoes are most likely to occur. Now, if you see an image that looks like this on radar, and your house or your location is up here, you're not going to see anything except rain. If you're over here, you're not going to see much either, because the rain's going to move over you and you're not going to see this. You can see, though, that the place to be is to the south and to the east of the thunderstorm. That's going to give you the best view. Now, you're a fixed location. You can't change that. So you're just stuck with that kind of view. But if you're looking at radar and you've got your house located on the radar map and you see where it's moving, you may be able to tell that you're going to go through the part of the storm where the hail is. Now let's take an example. Let's put ourselves right here. So we're at home and we're right here, and it's a spring day. We're experiencing a south to southeast wind. And it may be kind of a little bit breezy. It may be one of those days it's 15 to 20 miles an hour with, maybe some gusts to 30 out of the south and southeast. We look to the southwest from our view, and we see pretty black mass, dark mass coming at us. As we get, and I can't move this, so we move our house, and our house comes here, and now suddenly we get under the gust front. What does that mean? Well, we were experiencing southeast or south wind, 20 miles an hour, and then all of a sudden the wind changes direction, blowing out of the southwest or maybe west, and it may pick up. Instead of 15 to 20, it may be 30 to 35 with gusts to 45. So it picks up pretty good, and this is the gust front, because the heavy rain is bringing air to the ground and pushing it out ahead of the thunderstorm. Then, as the thunderstorm gets closer, we begin to get some light rain. If you happen to be in a vehicle, this is a case where you may need windshield wipers or intermittent windshield wipers. And then pretty soon you get into moderate and heavy rain, where the windshield wipers just don't go fast enough at all. You kind of wish that GM or whatever had stuck another speed in there that would go even faster, like southeastern storm speed. That's what I need. Okay, now all of a sudden you get into an area where you've got hail and rain mixed. And it may not be large hail, maybe... No, I'm not going to say marble-size hail, am I? No, okay. You may get into some quarter-size hail, And then all of a sudden, the rain stops, and you start getting into larger hail. By the way, I don't know if any of you were watching the storm chase the other day, Wednesday, but Megan and I had a really interesting experience on Alabama 77. As we're moving south, we were in heavy rain with no hail whatsoever. And then as we continued to drive south, we were in hail and rain, but it was becoming more hail and less rain, but it still wasn't large hail. It wasn't what I would call large hail. Then the rain really tapered off, but it was still raining, and we're getting about 1 inch hail. And by the way, anybody want to guess what shape the hailstones were at that point? Round, okay. Anybody else? Believe it or not, they were flat. Imagine a quarter. Well, that's what it looked like, except if you could have just made a little cup out of the middle, kind of concave or, concave in the middle of the quarter to where it kind of looks like your hand cupped. It was almost like a little cup, but the hailstones were flat. And that's what usually happens with raindrops in thunderstorms. As they fall, they actually are flat. Then we stop the rain and we're getting 1 inch, maybe 1 1/4 inch hail. And then the hail stops. So we pulled out from the curb, we pulled out from the shoulder, get on the highway, we're still headed south. All of a sudden, we hear, and pardon me, we hear, wham! Was that loud enough? Okay. It was so loud, I thought our chaser had been hit by another vehicle. I really did. I thought we'd been hit by another car. And then Megan points over to the side of the road, and the ditch, which was filled with water, is getting these tremendous splashes that were kicking up at least 3 feet high. And it's like, oh my God, we're now in large hail. And I mean large hail. This is the largest hail in 50.6 years of being a meteorologist. This is the largest hail I've ever seen in my life. It was slightly larger. It was probably about 2 inch, slightly larger than golf balls. By the way, we're requisitioning a golf ball for the chaser so that I have a reference point, because we didn't have a golf ball. So we're going to have a golf ball in the future, all right? So anyway, you can go on abc3340.com and you can see our hailstone picture. It was very thrilling. Scared me to death. And then we got hail for probably about, what was that, James? About 8-10 minutes? I think, and I mean, when it was hitting, I won't do that loud one again, okay? But when it's hitting the chaser, it was very loud. And then the hail finally quit. And then we took off to try to catch up with the storm, which is very hard to do. Okay, then when you get out of the hail, you get into a rain-free base area, and you see the tornado. So that's the way it might look in a series. Now let's look at some supercells from a distance. And these are going to be the visual pictures to help you try to identify those characteristics. So here's our supercell. We're a long way from it, so we can't see anything down near the ground. We can see the main storm towers. We know that they're right here. Here's the anvil. It's not a terribly well-developed anvil, okay? It's developing. I mean, it's a big enough anvil that this pilot is giving a very broad berth, wide berth to this thing. So he's giving it a lot of room. I don't blame him, okay? Here's another one where we've got the main storm towers. Again, we're too far away to see this down here. We've got the main storm towers. This is the anvil, and this is what's called the back shear anvil. This is the back side. And what's interesting is there's a lot of air coming into from the ground all the way up in this updraft. There's a lot of air coming in at all altitudes. As a matter of fact, there is so much air coming into this updraft that it can't really take it all and blow it downstream. So what happens is some of the air actually travels back against the flow, because the flow aloft is this direction into the screen. Some of that actually turns back, and that's what produces this back shear anvil, because some of that air can't follow the main flow, and it pushes back against the flow, producing this little bit of a cloud deck. Now this is a great example right here. This is I call this my optometrist slide because this shows you two supercells, supercell number 1 and supercell number 2. Supercell number 1, supercell number 2. That's what my optometrist does to me all the time. So anyway, here's the anvil for this one being blown into the screen. There's the main storm towers. We can't see the near ground features. Here's the anvil for this one being blown into the screen. Here's the main storm towers. And what's interesting is this illustrates the isolated nature of supercells. They tend to be very isolated storms. This storm has no idea this storm exists. They've each got their little chunk of the atmosphere where they're feeding off of warm, moist air, but they're not feeding and interfering with one another. So, like I said, this thunderstorm knows nothing about this one. Now, if these two get too close together, I can tell you what will happen. This one, being the northernmost one, will die because this one will be eating all the warm, moist air, so that can't get into this one, so this supercell will die. So when you're looking on radar, you oftentimes will see supercells that do get closer together, and then all of a sudden the northernmost supercell begins to diminish rapidly because the southern one is going to take over and take all the energy out of the atmosphere away from the northern one. Here's what Mamatis clouds look like. Everywhere you see a pouch, you've got some downward motion. Between the pouches, you've got upward motion. Tremendous turbulence in here. If you're a pilot, you avoid this like the plague. It'll rip your wings right off. So you don't want to go anywhere near that. All right, show you the diagram here. And very quickly, I'd like to go through some images, the way storm spotters saw them, of a supercell. Now keep in mind, we are going to be located right about here. So we're looking west, maybe a little west-northwest. So that puts the main downdraft off to our north and northeast, and the rain-free base is clearly visible. But before we do that, I want to show you two radar images. This is the radar image of, actually, if you'll notice up here, it's April 9th, 1998 at 0058Z. So it's, what is that, James? Was that daylight time? Yeah, it was daylight time. That was 8 o'clock, or a little after 8 o'clock. And notice here is the intense downdraft. Here's the mesocyclone right in here with rotation that is actually wrapping the rain around the mesocyclone right in here. And if there is a tornado, it's going to be right down in here. In this case, if there is, there was. Okay, but I didn't know that. I didn't know that yet. Now, I apologize here for the next slide because it's what we refer to as a 4-panel velocity. So it looks like this. Basically, this is the same elevation as this. So we've got this velocity, then we go up one volume scan to the next higher volume scan. This is the one above this one, and then this one is the one above this. So let's just take this one first. The radar is located down here. So the radar beam is coming out this way, away from the radar. Now let me explain something about a Doppler radar beam. If I'm the Doppler radar and I'm sending a beam down this aisle, the velocities that I can see are motion away from me and motion coming at me. If there's motion this way or there's motion that way, I can't see it. It's zero. So if all the air down this hallway was moving from left to right at 100 miles an hour, the radar would paint it as zero because it can't see anything. The water droplets have to be moving away or toward the radar. Can't be moving perpendicular to the radar beam. So the reds are motion away from the radar. So the radar's down here. So here is pink, which is the highest, actually the highest velocity we can get, motion away from the radar. Immediately adjacent to that is green and cyan, and those are the highest velocities toward the radar. So it doesn't take a rocket scientist to figure out we have a rotation in there. Now, I'm showing you the 4-panel because one of the things meteorologists look for is we look for a mesocyclone down low, but then we look above that for another mesocyclone, and that proves that there's continuity, which means this rotation extends up another 2,000, 3,000 feet to this level, and if you'll notice, it extends up another 2,000 or 3,000 feet to this level, and it actually extends up another 2,000 or 3,000 feet to this level. What that tells a meteorologist is that we have continuity. We don't have just a little mesocyclone that is aloft with no vertical continuity. We have strong vertical continuity here, and as a result, I'm pretty confident that there's a tornado occurring at the ground. All right? I don't know, but I'm confident because of what the radar is telling us. So let's put ourselves in the picture. Remember the diagram. We're looking west is the middle of the picture here. So what can we identify? Well, we're very close. So we're seeing the rain-free base, but we can't see features aloft. We can't see the anvil. The main storm tower is obviously in here, but we can't see it because of all the low clouds. So we've got our rain-free base right here. We've got the heavy rain. Remember, I know we're looking to the west, so the heavy rain is to the north and northeast of us. We've got from this point right around here, we've got a lowering. Well, if I draw a line from here all the way across like this, that's the rain-free base. So from here all the way over to here, it's lower. Is it a wall cloud? Well, I don't know. It's kind of broad, so it's kind of big. Wall clouds, if they're there, are usually fairly concise. Now, every wall cloud is going to have some clues to help you. This one has some clues. You see all the raggedness that you see here? You see this little poochy cloud right here, and there's some raggedness over here. All of that raggedness can help you identify if rotation is occurring. And I want to draw a particular attention to this right here. Because if you go down to the Galleria and you ask 100 people to describe a tornado, they're going to use the terms, probably 98% of the time, V-shaped or funnel-shaped. So this could get reported erroneously. It is not a funnel cloud or a developing tornado, but it is a V-shaped cloud, but it is what we refer to sometimes as scud clouds. All of these ragged clouds you see here are scud clouds. So we're going to watch that one because in the next picture, it's over here. So To the north and northeast, we have heavy rain. We're getting a hail report, by the way, right at this time. The hail's right in this area, right in here, and it's baseball-size hail. We've got our rain-free base right here. Now we have a definite wall cloud, much more concise, much more, developed. We've also got ragged clouds here, here, here. Remember, this one started over here, and it's actually rotated around to the north side of the wall cloud. And now, right here, we do have a special cloud. It is indeed a funnel cloud. Funnel cloud is defined as a violently rotating column of air not in contact with the ground. So air is not reaching the ground over here. We can see there's no debris cloud. So at this point, we probably don't care about the hail, and we probably don't care about the heavy rain, and we probably don't care about the rain-free base and the wall cloud because we've got something developing at this point. We advance in time, and with the help of telephoto lens, we can still see the heavy rain. We've got the rain-free base. We've got the ragged wall cloud that is very ragged. All of these ragged pieces helping you to see that it is indeed rotating. That is, this air right here is moving into the screen. This air over here is moving out of the screen. And now we have, well, is that a tornado or a funnel? Okay, I think most people said funnel. That's what I heard first. Then I heard a few tornadoes. Well, the truth is it's actually a tornado because look at the ground. There's a weak shadow. It's hard to see, but there's a little shadow. There is actually a debris cloud down there at the ground. Now, there is a connection between this and the ground, but it's air. What color is air? We can't see it. Something has to make the air visible. Debris and condensation are not yet making the funnel visible all the way to the ground. We advance in time, and now, is there any question at all? Is there any doubt? No. We have a visible funnel all the way to the ground. We can also see the debris cloud. Again, we've got our rain-free base. We've got our ragged wall cloud. And notice how bright it is over here. This is something we'll talk about this afternoon in the advanced session. It's called the the rear flank downdraft. I got rain-free base on my mind. Rear flank downdraft. And that plays a special role and actually may be very important into the development of tornadoes. So we'll talk about that this afternoon because it's getting a little beyond where we are right now. All right, we advance in time, and oftentimes tornadoes do just like this one did. It starts small, begins to grow, reaches its maximum intensity, stays at its maximum intensity for some distance. And if you've been watching carefully, it's been getting very fuzzy behind the tornado. And that's because, thanks to the rotation of the updraft and the broader mesocyclone, the rain is wrapping around from the north side to the west side to the south side of the tornado. And with time, it wraps all the way around. Now, the tornado is still visible right in here. It's very difficult to see, but it's still in there. Now the rain has wrapped all the way around. This is one of the reasons why we like to have lots of storm spotters, because your view may be obscured, but maybe her view is not. Maybe she's in a different location that's more north and has a better view than my view, which is from the east looking to the west. So she may be able to see it better than I can. So we like to have spotters in lots of locations. This is the way the tornado looked as it was decreasing in intensity. They often shrink into what's referred to as the rope stage. This is off the ground. Damage was no longer being done by this tornado, but you can see the tremendous damage that it did as it moves through this park in this town in Oklahoma. All right, now what I'd like to do is to try to put you in the picture. So this is where we get a little audience participation going. And what I'm going to do is show you a picture, and there's a clue. It's a rain-free base. So you don't have to guess. There's the rain-free base. But the question I want to ask about each picture is, you're the photographer, you're the spotter, what direction are you looking? So what that means is you have to figure out some stuff. Now, we took a show of hands a little while ago, and about half of you have been to previous classes. I'm going to ask the half that has been to previous classes to not shout out the answer, okay? Because you've been to it, so you know. So that gives the new ones a chance to know what's going on here, okay? So we've got a rain-free base. Do you want to identify some things? Let's identify some things. What's this over here? Rain, the downdraft, right? The heavy rain, all right? We've got the rain-free base. Now, we've got 1 lump, 2 lumps, 3 lumps, 4 lumps. What are those? I heard somebody say flanking line. That's correct. Flanking line extends what direction? Southwest. Yeah, southwest. So, with all of that, here's the rain-free base. What direction is the middle of the picture? Not quite east. South. And I heard somebody say southeast. Southeast is okay. What's happened here, of course, is we are looking south in the middle of the picture. The rain has moved off to our east. Okay, so it's off to our east because we're looking south. West would be over this way. Southwest is indeed the direction that the flanking line is stretching. All right, let's take a look at another one. All right, now this one has a few other things we can identify. We can identify, as the title says here, here's the rain-free base. What's this? It's the rain, yes. The rain is in the downdraft. Yes, downdraft. Now, the rain-free base is the base of the updraft. And actually, if you look very closely, we can see the edge of the main storm tower. The main storm tower is right in here. And then here's 1, 2. We don't really see a third one. What are these? Flanking line, yes. So, what direction is the middle of the picture? West, yes, west. Now, there is something else in the picture. What's this? That's what I wanted you to say. It's not. This is what can fool people. The photographer who was taking this picture made notes, and actually what he did, and as a storm spotter, this is what you should do. When you see something that you're suspicious of, you need to watch it for a period of time. And he did just that, and as a result, he was able to identify that this was a little bit of rain, forming a little bit of a rain shaft in an area where there shouldn't be any rain falling, but there is a little bit of rain falling, and it's making a V-shaped cloud. But he said it was very obvious that this was falling down, and it was like you could see downward motion in the whole thing. There was no evidence of rotation. So as a storm spotter, you'd want to be very careful. You don't want to see something, jump to a conclusion, and call it in. Because if I was a meteorologist and this up here, radar was showing me a mesocyclone up here, and somebody reports a tornado here, 1 and 1 equals 2. So I would be compelled at this point, with a tornado reported and an updraft with a rotation, I would be compelled to issue a tornado warning. But it would be in error because this is not a tornado, okay? Nature makes things hard on us. All right, a little bit different. It's still rain-free base. What direction are we looking? Yeah, it's quiet. I can hear the crickets chirping because it's hard. I know. What's this up here? Rain. It's the downdraft, okay? The downdraft is typically to the northeast. What direction are we looking in the middle of the picture? No, it's north. You're looking north. This one looks different because the rain-free base is overhead. Keep in mind that a thunderstorm is dynamic. So when the rain-free base is off in the west to us and it moves over us, it's going to look different. All right, now we're going to change gears. This is wall cloud. So here's the wall cloud right in here. What direction are we looking in the middle of the picture? Come on now. Come on. No. What's this? That's the rain. The rain is to the north and northeast. So what direction is this? North, yes. Now, do you get the sense that this picture, still picture, do you get the sense that this might be some rotation? Yes, and it was. All of the ragged clouds that you see all can help. Now, one of the things you may see is you may see condensation occur at a slightly lower altitude here, and the cloud, the little cloud that forms, actually move up. Because remember, the rain-free base and the wall cloud are under the main updraft, the main towering updraft of the thunderstorm, and the wall cloud is under the strongest upward moving air. So as air is coming into the wall cloud, you may actually see some clouds form at a slightly lower altitude and move up into the wall cloud. When you see that, you definitely are in the right place because you're watching where the updraft is occurring and where the wall cloud is. Maybe it's not a wall cloud. Maybe it's just the rain-free base. All right, another wall cloud. Here's the wall cloud here. Rain-free base. What's this over here? Rain, downdraft. All right. Now this has a beaver's tail. I'll explain that in a minute. But what direction is the middle of the picture? West. Yes, very good. Now I'm going to explain the beaver's tail. This is the beaver's tail. Here's the wall cloud right here. All of this is essentially a beaver's tail. What's happening is some of this cold, wet air, or cool, wet air, is actually coming back and feeding up into the updraft. And you can see there's a cloud right here, there's another one here, another one there, another one here. This is just simply some condensation because this air is cool and wet, which means it doesn't have to rise very far before you get some condensation. So you actually get sort of a dotted line, and then you get solid condensation as the air is rising and coming back into the wall cloud and up into the updraft. So you get these beaver's tail from time to time. It's not something you need to spend a lot of time looking for in the southeast, okay? We have them, but they're not something you need to really be worrying for. All right. Now, this one is perhaps the hardest of all the pictures at this point. You are looking at a wall cloud right here. And I will give you a quick clue. First of all, I took the picture, so I do know what direction this is. And we're looking for the direction into the middle of the picture here. And I will give you a clue. You see the wet ground? That's because it just rained here, and the rain is over here. Okay, so what direction are we looking? Southeast is excellent, yes. If you said south, I wouldn't argue with south, but you are looking southeast. Now, remember I said earlier that when you see a wall cloud, you want to look for rotation, and ragged clouds can help you. Well, in this case, they did. On this side over here, you see all these ragged clouds right here? Those clouds are actually rotating toward me and sort of this way, okay? So they're rotating from south to north. These ragged clouds that you see over here were actually rotating into the picture away from me. Now, this is where storm spotter reports became absolutely critical. This wall cloud had been observed over Montevallo, which is back this direction, in the southwestern part of Shelby County. And the National Weather Service did not, I repeat, did not issue a tornado warning. Why not? Because the Montevallo Police Department was reporting this wall cloud with rotation and the absence of anything coming out of it. They followed it for several miles in the southwest part of the county. Additional spotters were seeing it. I was calling in, telling them what I was seeing, and they basically had a tornado warning ready to go for Shelby County, but they didn't hit the button because there was nothing coming out of the base of it. Yes, there was a mesocyclone up here. They were seeing that clearly. We had rotating wall cloud, but because of the absence of anything coming out of it, they elected not to warn. Very good, and that's where reports become very, very important. All right, now we're going to change gears just a little bit. You're going to see a sign that says tornado. It really isn't true. I want you to determine, is this a tornado or a funnel cloud? Okay. Have you been to class before? Okay. Yes, he said it's you can't tell because of the trees, and he's absolutely right. From our view and from what we can see, our guess is that it is a funnel cloud. But do we know that for sure? No, we don't, because the trees are blocking our view. So what do you report? I mean, we want you to report. You may be the only person seeing this. We definitely want you to report. So what do you report? Well, your report should be something like, I'm observing what I believe to be a funnel, but I cannot see the ground. I don't know if there's a debris cloud. Perfectly good report. Excellent report. Lets the meteorologist know. Let's take two scenarios. What if you called in and said, hey, this is Brian, I'm southwest of Montevallo, and I've got a tornado. What did I just communicate? That damage is occurring. I can't tell that for sure. That's really erroneous. Okay, so we'll take another scenario. Hey, this is Brian, I'm southwest of Montevallo. I've got a funnel cloud. What did I just communicate? That there's no damage going. Do I know that for sure? No, I don't. That's why a report that shows some uncertainty is fine. All right, what about this one? Tornado or funnel? I hear a few funnels. Okay. You guys are very, very quiet. Funnel. Now, does the rotating air stop here or here or here? I have no idea. but it doesn't get to the ground. There's no debris cloud down here. So the visible funnel stops right there. Rotating air may extend further down, but it does not extend to the ground. Have a clear view of the horizon, no debris. All right, what about this one? See, I give you an easy one. Interesting, the debris cloud is actually coming up pretty high on this side and being spread way out on this side. I suspect it's moving over a plowed field. All right, what about this one? Is it a tornado or a funnel? Tornado. And what's making the tornado visible? Debris, yes. All right. This happens to be a north central Texas tornado in late December. And most of what you see here is grass and leaves. All right. But to give you an idea of how nature can make it difficult on you, in less than 2 minutes it looked like this. And what's this? It's mostly condensation now. But it's pretty obvious it's on the ground. It did not hit this house. It was moving, actually it was moving over this way. So it was not coming at us. All right, what about this one? Tornado or funnel? Tornado. What's this? Rain. Yes, absolutely. Is that a concern? You're darn right it is, because it can come around and wrap around, and now my view is once again limited. One of the other reasons, like I said earlier, one of the reasons we like to have spotters in many locations, okay? All right, you've seen this one already, but this was a really classic example here. One of the reasons that this tornado looks white is if you were the photographer and you panned over this way, and I don't mean very far, just a short distance over here, what you would see is clear blue sky and the sun setting. So the sun's rays are coming in under the base of this thunderstorm, lighting up the tornado, the wall cloud, the beaver's tail, and the debris cloud. Very, very well lighted scenario, okay? I wished I'd been there. It would have been tremendous to view this event. This tornado was actually on the ground for approximately 60 miles, and it never once crossed the city limits of Jonesboro, Arkansas. Jonesboro, Arkansas is just back up this way because we're actually looking kind of west-northwest. So Jonesboro, Arkansas is back up this way. So what caused $20 million in property damage in Jonesboro, Arkansas? Okay. Hail. The hail, this is to the north up here. This is where the hail was. Hail on the order of baseball size caused a lot of roof damage, and it caused $20 million in property damage inside the city of Jonesboro, even though the tornado never actually hit town. All right, this one is actually an Alabama tornado. I can't tell. Can you? Okay, trees blocking our view. So, what do we report? Well, we report the same sort of thing. It looks like it might be a tornado, but I can't really see for sure. Or I think it's a tornado, but I can't see for sure, so I don't know. Now, we've got a little gap over here that's going to be helpful. We advance a little bit in time. It hasn't reached our gap yet, but it's looking a little more obvious, isn't it? And then it gets into our gap, and now, boom, it's down. It's definitely down. And it was down back here. I know that because of the tornado track, but notice the blue sky to the southwest. This is the tornado that hit Cottondale and the eastern side of Tuscaloosa County. And actually, if you remember, in Cottondale, it destroyed a food world. One of the interesting things was that one of the cars in the parking lot was picked up and thrown through the roof of the food world. I was very mad at food world officials because they wouldn't let me go inside. I wanted to see that car hanging. And by the way, I found out, I actually met a guy that was in the food world when the tornado occurred with his son. And I met him like about, 6 months later, I think. And I met him over at Reform. And I said, well, you've got to answer a question for me since you were in there. Did the car actually come all the way to the floor? And he said, no, believe it or not, the car came through the roof, and with all the wiring and telephone wires and everything that was in there, the car actually stopped 6 feet above the floor. So it didn't actually crash all the way to the ground inside. It was suspended by all the stuff that's in the roofs. So kind of interesting. So I was able to answer my question. All right, quickly, tornado safety. We want you to be safe. And then we'll look at some videos here. 2 tornado rules. Get away from upper floors, get to the lowest floor possible. That's rule number 1. Once you're on the lowest floor, you want to put as many walls between yourself and the outside. So this family of 4 here had decided on a closet that was below the stairway that led upstairs. This is what this house looked like prior to the tornado hitting it. This is what it looked like after. There's no safe place to be. There's only one wall standing up here. And again, they had gotten to the closet downstairs. Car safety is a topic of considerable controversy. There are people who say you shouldn't do this and you shouldn't do that and you should do something else, and I disagree with all of them, so, I'm just disagreeable. Tornado safety, I think, is sort of two parts. The first part is, as the driver, you need to decide where the tornado is moving. How do you do that? Well, if you're stopped and you see a tornado ahead of you and it's getting smaller, it's moving away from you, okay? What do? Well, you just pull off the shoulder and stop. Don't do anything, because you may go down the road and it turns this way and then comes back around and you end up in the path. So you don't do anything. All right, the tornado is not changing size. It means it's either moving across your view or across your view this way. What do? Same thing. Don't do anything. Stop, let it go. All right, and you're safe. Now, worst case scenario, you see a tornado ahead of you and it's getting bigger. What does that mean? Yeah, that means you're in deep trouble. Okay, that's what it means. All right, now at this point, you have two choices. You can either try to be safe and work for safety, or you can die. I mean, it's your choice. If you want to die, stay in the vehicle. If the tornado hits your vehicle, you will die. I'm not going to make, as my father used to say, mincemeat out of it. I'm going to tell you the truth. You're going to die. I've seen cars a lot worse than this that are tossed many hundreds of yards and you could not survive. So, what do? Well, the first thing to do is to get into a substantial structure. That's the number one choice, if you have one. I drive on the interstates a lot. Shelby County, down I-65. There's no places to go. There's no structures to get into. And the nearest rest area is down in Chilton County, right? So I can't get there. All right. So what do? I get into a ditch or depression. You want to leave the vehicle, get from it, as far from it as you can, and get into a ditch or depression, something to put your body below ground level. There are stories galore of people surviving by doing just that. Is that going to be fun? No, it's not going to be fun. And you may find yourself in a ditch with some snakes. One problem at a time. You've got to survive the tornado first. And I don't think the snakes are going to worry about sharing their shelter with you, okay? So the bottom line is, don't stay in vehicles. And I want to tell you, one of the controversies is with a professor at, Kent State. I don't know how this guy observes things, but I wouldn't trust it. He basically visited the Piedmont, Alabama, and the Georgia area that was struck by the Piedmont tornado 2 weeks after the tornado event. And I was on a CBS program with him remotely from here, and he was in Kent State and through New York. And his solution was that people would have survived if they'd gotten in cars. He doesn't want you to go anywhere. He just wants you to get in your car. And it's kind of like, what? And he said, well, we were there after the tornado, and we observed many cases where the mobile homes were destroyed and the cars were fine. And it's like, what? Do you know where that car was 2 weeks ago? I don't know where that car was 2 weeks ago. You can't possibly know. And so he counters with, well, if you're in a car, you have airbags. No, you don't. You don't have airbags if you don't turn the car on. You've got to turn the car on for the airbags to activate. I can prove that. My Avalanche right down there. When you turn the key, the airbag activates. Okay? You can't be in the car just sitting there with the ignition off and have the airbags work. Okay? So, controversial though it may be, leave the vehicle, get into a ditch of depression. Now, I do want to say that I actually think I ran into a relative of James Spann many, many, many years ago. I was giving a talk at a 5th grade class, and I made a mistake. I said the safest place in this picture was on the ground floor of this house in that closet. I had a gentleman on the front row, I'm sure was related to James Spann, point out to me that the safest place in the picture is this house across the street. And that's honest, that is honest truth. put a stack of Bibles out here. That did happen. And I remembered what I said, the safest place in this slide. I did. I made a mistake. All right. What to report? Tornadoes, hail, ½ inch or bigger. We really don't need to know about small hail because small hail is pretty universal in a lot of thunderstorms. So we really don't need to know about it. I know everybody wants to report, and I understand that. I'm the same way. You know, I'm trying to bring back visual images for you all to see, and I want to get some, but report only ½ inch and larger because we tend to get a lot of hail reports, okay? Please report relative to known sizes. Do not report marble size hail. There is no standard size marble. When I lived in Vermont as a young guy, I used to be a pretty good marble shooter. And I had some that were as small as the end of your finger, your little finger, to one that was my shooter marble that was 2 inches in diameter. All right? So if you say marble, I have no idea what size you're talking about, okay? I really don't. So relative to coin sizes, dime, nickel, dime is 3/4 of an inch, nickel's 88/100ths. Quarter is 1 inch, okay? Quarter is a great size. When you start getting above that, known sizes, ping pong ball, 1.25 inch, 1.25 to 1.5 inches. Golf ball, 1 3/4 inches. If you got a measuring device, 2 inches in diameter, that sounds great. I mean, no mistakes there, okay? Now, when I first came to Alabama in 1989, I was working my first severe weather event, and I had a great phone call. It was from a dispatcher in one of our counties here in central Alabama. And the dispatcher was really wanting to report, and she said, and I quote, "We have large hail." Okay. Could you be a little more specific, ma'am? What do you mean by large? And there was this pause, and the lady, bless her heart, said, "Oh, about the size of hen eggs." And I so bad wanted to ask, is that small, medium, or large eggs? But I didn't. I still didn't know how big the hail was. I mean, because they're small, medium, and large eggs, right? Okay. If you take pictures, be sure to throw something in the picture that's a known size. If you take it on your hand is okay because we can kind of guess at how big your hand is. But if you have something like a quarter, something you can throw in the picture, even if they're really big, if you throw something that gives a reference, and that really helps. We want to know about wind damage. Don't worry about whether it's been a tornado or straight line wind. We'll figure that out later. Flash flooding or flooding that's occurring, and if you have rain because you have a weather station, we always love to know the amount. Now, where do you report? You can report directly to the National Weather Service. They have an 800 number that's available. Local law enforcement will get your reports to the Weather Service. Local emergency management will get your reports to the Weather Service. Local media outlet like ABC 3340 will get your reports to the National Weather Service. As a last resort, if you don't have any of these, you can use 911, but we want this to be a last choice because 911 is really reserved for life-threatening situations. Now, the tornado may be life-threatening at the time you see it, and it may be a good call to call 911. But to give you an idea, on March 27th, 1994, the Piedmont tornado, the Calhoun County, and I'm not criticizing. This is a fact. Calhoun County 911 received 80 reports of the tornado. 80. How many of those reached my office at the Shelby County Airport? Yes. None. Yeah, I heard none over here. You're correct. None. We changed that. I changed that after that. I started going to all 911 centers saying, listen, we know you don't want to be bothered with these reports, but when you get them, we need them. We don't need all of them. I told the Calhoun County people, we don't need all 80 reports. The one that's important, the first one. That's the one we need. That's the report we need. So, 911 last choice. Now, if you really are going to be using 3340 and Slack, the best thing you can do is, James will know exactly where your report is if you just reference the nearest barbecue joint. All right. Sorry, I always forget to introduce. Now, we're going to put all this in motion. It's always hard to get really good videos, so they're not always absolutely clear. And there is no audio with any of these because people who videotape or shoot video of tornadoes, they have a tendency to cuss a lot, okay? So it's just, this is a family-friendly show, so I kind of just leave the audio out. But besides that, for most of it, it's mostly just loud, okay? So this is a storm chaser, actually in Mississippi, believe it or not. I want you to really concentrate on the rotation. That's why I'm showing some videos, is to try to put this in motion for you. I want to clarify too, these flashes are not transformers exploding. These are where power lines are arcing together because of the wind, okay? So it's not transformers exploding. That arcing may help you at night because you may be able to see that. I know the April 8th, 98 tornado, they said that the arcing of power lines and the flashes that they were seeing were very helpful in knowing there was a tornado, because that tornado occurred primarily in the dark hours after 7:30, between 7:30 and 8:30, and so it was pretty dark. And one of the storm spotters that I had actually trained was within 3/4 of a mile of that tornado, and he never saw it. He heard it, he saw flashes, but he never saw the tornado himself because it was dark. All right, I'm going to move on to another one. I show this one because a lot of people want to know, how fast does a tornado develop? Well, look how rapidly this is coming down. I also show this because if you're going to shoot video, please try to have a tripod, okay? It helps to be able to see. Now, we do have a problem. We've got a tree line here, don't we? Now, indeed, at some point in here, not on the big screen because it's fine, but you can see debris in here. So actually, we do know that it is down on the ground because we're getting debris. You can see some of that debris here towards the end of this video right in here. Again, it's hard to see because of the motion. He's very excited. I think he cussed a number of times, okay? All right. Now, this one is very interesting because you can see condensation. Remember, this is turning this way, so air is coming at us on this side, and you notice we're getting condensation as the air comes into and rises up into the updraft of the mesocyclone, which the tornado is growing out of. Here's an example here where you're going to see this motion that's coming around. The air is coming around, feeding our direction, but also rising up. You see condensation occurring at a low altitude, but it's rising up. This one almost looks like a second tornado, but it's not. It's just simply condensation that's occurring rapidly as that air is moving upward extremely fast. Another reason I don't like to show or play the audio is this particular videographer said to somebody who was with him that he was hoping he could sell this to the radio station. And it's like, what? Why would a radio station buy video? I have no idea. But anyway, the thing is, we don't always have professional film crews out there to film this stuff, okay? So we have to take what we can get. This one is very interesting here. This is a Stuart Robinson, an English storm chaser. And what's interesting here is, if you watch closely at the ground, of course you can see the debris, which is mostly water, I think. But notice that the tornado doesn't move much. This tornado is close to stationary. It does begin to move at one point. But notice, it has not moved here. And I think there's a pond or something in here that this is all water, I think, and it's creating a very big debris cloud that I'm not sure, it doesn't look very thick. Now there it's destroying something. It's now beginning to move. And look at that debris. It's probably pretty light debris, but it's moving around it very rapidly. And this one also shows something else, and that is every once in a while, a stupid person will drive by. Watch carefully right in here, and you'll see one of those here in a minute. Here's a tornado that can't be more, there it goes. See? I mean, it's like, what? You don't know, you don't have any idea what's happening. Just I don't know if that's east, west, north, what, but you don't know. And then just, top it off, here comes another one right there. Now, the only thing is that guy's got an instrument rack on. It might be a storm chaser, I'm not sure, from a university. Anyway, he goes back, and you can see a huge funnel right here with a lot of debris, which is primarily water. Now, this one is also interesting because you can very clearly see the rotation, and the rotation is primarily dirt. But you also notice there's an absence of any kind of visible funnel. When he does pan back in just a second, you will see the visible condensation funnel aloft. There it is. There's a connection all the way down here, even though it's not visible. but there's a tremendous debris cloud. I don't know if it's so much that the wind is that fast, but it's definitely picking up a lot of dirt. I guess you could call this a dirty tornado. All right. Now, I want you to watch this one again. The rotation is what we're focused on, but watch this house right here. Oh, no, you haven't seen anything yet. Okay, just wait. Okay. This house right here. All right. 1, 2, 3. Wizard of Oz. Notice the condensation that's actually occurring. The air is moving across the highway so fast, we're getting condensation occurring at the ground. I mean, just within a foot of the asphalt. Almost looks like it's coming at us, doesn't it? Well, the rotation is working its way around. Again, tremendous, tremendous debris cloud. All right, very quickly, and I'm going to show one more video. It's a fairly extensive video. It's about 5 minutes or so, 6 minutes. I'm putting it at the end because it is the Tuscaloosa tornado from April 27, 2011. And if any of you are from that area and are very sensitive, I'm very sensitive about that tornado. So if you're sensitive about it and you do not want to see it, because the truth is that the video, as it's being shown, there are people dying. There's no doubt about that. I'm choosing to show the video primarily because, number one, it's excellent video. John Brown, are you here? Okay. He was going to try to make it, but I guess he's not here. John Brown, one of our sky watchers, shot this video from 2059, and he's only within, what would we say, James, about a mile or two? Is it as much as 2 miles? About a mile. Okay, he's very close to it. So I'm giving you a heads up, and if anybody wants to leave before then, I understand. James will talk, and we will break for lunch for an hour and then start back. Okay, but I want to give you this URL. I can't remember it, so please write it down. It's hard to find. The National Weather Service hides things on their web pages, so I can tell you what it means. This means Office of Meteorology brochures, spotter guide, June 6th, 2011.pdf. Okay, I know what it means. And you'll see some of the diagrams that I've used today are part of the public domain, but the National Weather Service has them published in this field guide. And also, whoops, where did John's video go? Whoops. Okay, I knew it was in yours. All right. With that, very quickly, I'm not sure what the time is. Are we doing okay?
11 o'clock.
Oh, well, then we're right on schedule. Fabulous. Oh, I just got noticed that there's motion in my yard. I want to tell you one more James Spann story. But if you have any questions for me, I would be glad to try to answer them, so be thinking about them for a second. James got a fabulous cake a couple weeks ago. I mean, this cake, whoever baked this cake, they outdid themselves. It was a 3-tier cake. On top of the 3rd tier, it had this gorgeous, well-constructed gray tornado. It was fabulous. And James took a picture of it, and then I happened to look down a little bit, and they had a cookie of James Spann, with black pants and white shirt and red suspenders, standing right in front of the cake. But I happened to notice that there was a toothpick sticking out of his chest. And I thought, oh my God, he's been speared by debris. I wasn't smart enough to remember that I have a camera right here on my belt, and I didn't take a picture, so I can't prove it, but you have to trust me. That was true. Anybody have any questions for me? All right, then I'll turn it over to James. And I'll go start your presentation.
All right, everybody stand up. Let me just get that clicker. I need the clicker. Oh, everybody stand up. Stretch your legs. Stand up. Punch the person next. No, I'm just kidding. Give me 50 push-ups, 25 burpees. Let's go. No, just kidding. Now, I've started to work out. I've lost like 15 pounds, and I got 15 more pounds to go, but I've learned what burpees, forward lunges are, and all that kind of good stuff. But all right, have a seat. Thank you all. We're going to get you out of here for lunch really soon. By the way, just check the metrics, and the number of people reached on Facebook so far with this live stream is over 200,000. So thank you for watching the live stream. But what I'm going to do is go through a lot of stuff that's on my mind. I have been speaking in different parts of the country a lot. We're empty nesters. I don't know if anybody in this room is an empty nester. Like our kids are now kind of like, you know, for years I was at the ballpark this time of the year, and that's where a lot of people are today that wanted to be here. They're at the ballpark. I was at the ballpark. Our youngest played on through high school at Spain Park. But now that we're empty nesters, I have a little more freedom to do some conferences, and I speak a lot about issues that are very serious. And basically what you're going to get today, it's some inside baseball. This is stuff that's going on within the weather enterprise, but it's very important. And you know, it's funny, I've been speaking so many different places. I was in Chicago last month, but I'm thinking I've really not shared this here at home. So for those watching on the live stream and for those that are here, this stuff's pretty important for those of us in the weather enterprise. This is what my main talk is today. It's about where we are with this watch warning system. We're at a fork in the road, and I think if we don't do something within the next year or two, this thing might collapse. And this could be catastrophic, so my heart is in this, and I'm going to work very hard this year to spread the word, and we've got some things going on this summer. But before we do that, let's chase a few rabbits, okay? Has anybody ever seen this floating around the internet this week? I mean, this is like really sweet. I mean, it's very sweet. And I don't know who does these memes. I have no earthly... Brian, do you do these memes? No. I mean, somebody just... They're great. But this involves the event we had Wednesday, okay? This is the event we had Wednesday. And again, that's a really sweet little meme, and that's awesome, and that's cool. But let's go back and talk about the forecast for Wednesday. This was Wednesday, April 5th, just a few days ago. What we forecast morning storms that morning with hail and strong gusty winds, then kind of a lull during the midday hours. Then we forecast strong supercells that would be dangerous in the afternoon and evening hours. The Storm Prediction Center had a big moderate risk for about the eastern half of the state. So by the way, all modes of severe weather possible: large hail, damaging wind, and possibly a few tornadoes. So let's go back and look at what happened on April 5th, 2017. We had morning storms with hail and gusty winds, a midday lull, we had afternoon supercells, and we had all modes of severe weather reported. But everybody thinks it was a bad forecast. I mean, it is really bizarre. We're learning, we've got to know more about social science. And I think maybe, I don't know. But let me just show you here, this is, and here's how I deal with the haters. We deal with brutal vitriol. You don't even want to know the stuff we do. If you could walk a mile in my shoes, your head would explode. So the way I do it, Brian, I take just one at random, one hater, and just throw it out there for the world. And this happened to be the one that I chose this time. This was some lady, and what's weird, I actually learned this was actually from 2015. She's been hating on me for years. Lying, man. And trust me, there's a lot of stuff I can't show you from this person. But there's some public perception that it was a bad forecast. And I think maybe what didn't happen, we mentioned the potential for a few strong, violent, long-track tornadoes. And that didn't happen. And maybe they latched onto that. But for Lily Mae, this was the afternoon of April 5th. And maybe you didn't have a supercell at your house. But guess what? We had supercells that produced a lot of damage and human suffering that day. This is Springville in St. Clair County. That would ruin your day. It tore their house up. It tore their car up. It produced a lot of damage. This was extensive over about the eastern half of the state. And I think what's happened in society is it degrades. If it doesn't happen to me, then it doesn't happen at all. We are now in a self-centered society, which is really odd. And again, we're having to take this into account when it comes to social science and how we do forecast and warnings. But we just live in a different world. It is not the same world that we had when I grew up, and it was not the world we had 10 or 20 years ago. But this was a darn good forecast. And people say, well, we didn't have any tornadoes. Well, number one, I would be kind of happy if that was the case. But here's the problem. We did. And again, maybe it wasn't at your house. And that's what's so weird. If it didn't happen in Birmingham or some big city, then it doesn't matter. This is one of the tornadoes that day. This is the one that Brian was on. If you watch the live coverage, Brian and Megan were out on this storm. This is in Cleburne County. And again, you know, if it happened in a rural area, does it not matter? I think people that live in rural parts of the state are discriminated against. You know, if it happens in Birmingham, then it happened, but if it happened over here, it didn't happen at my house, it's no big deal. But anyway, I could talk about that all day. But this is astounding, and I think one of the things that maybe, while we didn't have the violent long-track tornadoes, and like Brian said, little things make a big difference, guys. Down here in the lowest level, that barb should probably be over to the southeast instead of the southwest. And if you look up here, the LCLs were a little high. They were almost 1,000 meters, so maybe the storms were a little high-based. The lower gates down here were out of the southwest instead of the southeast, but still, I think the forecast was very good that day. But let's move on. That's not why I'm here. This is me when I started in Birmingham. Wow. Worked at Channel 13. I came here in 1979. I was 23 years old. This is before y'all were born, okay? This was a long time ago. There were two people that did TV weather in Birmingham when I was coming along, Rosemary and Pat Gray. And I replaced Rosemary on Channel 13. I stayed there for 5 years. I was transferred to Dallas, and I looked like this in 1984. Wow. I floated this one out on social media last night. By the way, that was a comb over up here. I had no hair. That was a comb over from one side. But I spent a few years away in Dallas-Fort Worth, and you know, I'm glad I did that. I met some brilliant people in the weather enterprise that shaped my life, that changed me, and I saw some things I needed to see. There was an L-1011 plane crash in Dallas in 1985, in August. I was working the 6 o'clock news. I was on the air that night, and I watched a local station cover that event, and that station, WFAA, and how they did that shapes how I cover weather today. I mean, I had to loop through Dallas. It was just something that had to happen. But anyway, I was away for a couple of years, but other than that, I've been here the whole time. And this is really creepy. I think I've been here too long. I mean, this is just very disturbing on a lot of different counts.
And it's not me.
I was going to say, Brian lives in Helena, and wow. I'm a child of the 1970s. I was a senior in high school in 1974. This event would change my life. This was the super outbreak of tornadoes in 1974. A little town up here called Guin. Y'all ever heard of Guin? It was just almost taken out. It was, I think, in my lifetime, that's the most violent tornado in this state. 22 people were killed there. If you go into Guin today, there's a memorial in the town square for those that died. But we had about 80 deaths in our state that night. This was just a horrible situation. And my hobby then and still is today, ham radio. We have some ham radio operators here today. There were no cell phones in 1974. We were it. And by the way, if we have a tragedy today, your cell phone won't work. There's a good chance it will be useless. Ham radio operators are still just as important today as they were back in the 70s. But I spent 3 days away from high school. They allowed me that time off to volunteer, and I saw things that would change my life. My first station, my first position was at the emergency room at People's Hospital in Jasper. I saw things in that ER that changed my life. I've never talked about them publicly. I've never talked about them privately. I don't want to. But I saw things that maybe an 18 or a 17-year-old shouldn't see, but I saw it. And again, it's just something I think I had to experience. And as Brian's talked about, this is where we are today. And again, this number is a little skewed by what happened in 2011, but this is not where you want to be leading the way in the country. And we've got some work to do. We've got some work to do. You do and we do. And that's where my heart is today. And Brian's gone through all this. This is a repeat. I copied you, sir. I'm sorry. When I was in Chicago and had to rip off some of his graphics, but again, here we are, number one. And you don't want to be number one in this list. But let me just say this for everybody in this room, no matter what you do for a living, your cumulative knowledge and experience will lead you to a day or two in your life where it's all needed, good and bad. Everybody in this room, you've had things happen to you, and you wonder, why did this happen? And a lot of it's bad. But you have to have that experience that's going to lead you to 1 or 2 days. You'll only have 1 or 2 days in your whole life that will define who you are in your career and your life. And you know, my life, I've had good, like everybody else in here. We've all had baggage. We've all had good things and bad things happen. When I was in 2nd grade, my father abandoned me. I'm a fatherless child. My father walked away in the middle of the night one night. He just left, gone. No goodbye, no nothing. And all of a sudden, it was me and my mom, and I have no brothers and no sisters, and I became the man of the house at the age of 7. But let me tell you this, I learned one thing from that experience: hard work. I am not good at anything I do. I'm not. I'm really not. But I will work harder than anybody else in this room to accomplish a task. I learned that work ethic from that experience. But in my life, I think one of those days for me was what happened here 6 years ago. This is the generational tornado outbreak of April 27, 2011. In our state that day, we had 62 tornadoes. Then listen. The next time this happens, I will be at Elmwood, okay? People now, every time we have a severe weather event, will this be like April 27th? I don't like that question. Of course the answer is no, but how many does it take? One. For that to be your April 27th. If there's one tornado in the whole state, and if that sucker comes down your street, that's your April 27th. That's a bad question to ask. And this is not unprecedented. Again, the analog would be 1974, the super outbreak, April of 74. It was kind of like this. We had a day like this on March 21st, 1932, when Brian started working at the Weather Service, okay? Yeah, oh, trust me, I got some good ones for him. But goodness, every tornado has a story, and many of these were kind of famous. They got more attention than others. What's so sad, a lot of the tornadoes got no attention whatsoever that really needed to get attention. Out in these rural areas down here, the one that came through Greene and Hale County, hardly anybody talked about that. I'll drive through some of these paths today out in the country and still think about this day. This is the basic facts on the day. We had 62 tornadoes. And listen, that next number, that's the only number. If you were to open up my brain and see a number on my head, that's it. The only number that matters is that one. 252 people died. That's inexcusable for anybody in here. These were precious people that died. And we've got work to do, like I talked about. You've got work to do. We've got work to do. We all do. But that's insane. I thought the death toll that day should have been 30. 30 people, that's a tragedy in itself. But 222 people should be in this room with us today. We had 2 rounds of storms. The morning round was probably a little under forecast, but the warnings were just excellent. Listen, the physical science was remarkably good. The physical science could not be any better on this day. The work done by the Weather Enterprise, the National Weather Service, the media, everybody involved. What we learned that day is that maybe we're not that good at social science. Nobody in our business has any background, to my knowledge, in operational meteorology and behavioral science. My first major in college was electrical engineering, and I finished in meteorology. I've never taken a class to being some TV guy or, how people react to warnings. And we've got to be better at that. We have to be better at the social side of this. Synoptic scale setup, for those that never saw these maps, it was the classic synoptic scale setup. Surface low was down here southwest of Indianapolis. Very, very diffluent flow aloft with very howling wind fields. And again, this is what happened. This was the storm report, the LSR report coming from the guys in Norman. Look at some of the rotational tracks. A lot of you probably have seen the radar loops, and this is still horrifying today. You're looking at graphic violence. This is graphic violence. And what we have learned is this: most people, when they see this, the Joe Q public. Now listen, if you're at this thing on a Saturday in April, you're a weather dweeb, okay? You're just a nerd. You're a geek, which is cool. We all are. Joe Q public, they just see a bucket of spill paint. And we've learned that. We have to do a much better job of getting cameras on tornadoes. That's why Brian and Megan and all of our spotters in the field that help us are out there. Because if people see a live stream of a tornado, they'll do something. But again, this is horrifying. Anybody with any background, anybody that's meteorologically inclined, when you see this radar loop, it is absolutely horrifying. This is, again, one of the ones that got a lot of the attention this day. This was the supercell that formed over here on the other side of Meridian. Came all the way through the state, and we really don't know why. The tornado lifted, Fultondale, got back down in St. Clair County. What's interesting, where this tornado lifted, we had a tornado the next year in January 23rd of 2012, basically in that same little slot right there. Killed a 16-year-old girl in Clay. But whatever, this is just horrifying. But obviously Tuscaloosa, Birmingham, Shoal Creek Valley, Ohatchee, Webster's Chapel. And it lifted over here in North Carolina. That's what you call a violent long-track tornado. This was the Tuscaloosa tornado, and I have no joy in watching this. I don't spend a lot of time. Look, and let me just say this. What I'm saying right here doesn't matter. I mean, yeah, this is pretty riveting live local television, but what I say here doesn't matter. What I said 40 minutes before this happened is what matters. But this is the tornado coming through Rosedale Courts, as seen from the top of the Tuscaloosa County Courthouse. All this stuff's on YouTube. You guys can watch this, and you probably have. And again, we had the guys on the ground. And Brian mentioned John Brown and Mike Wilhelm. These two men have been trained for years and years and years and years and years. They come back and back and back and back to this event. And again, all of the training in their life led up to this day. They're perfectly safe. A car is a death trap, like Brian says. This, you know, these nitwits that say you get in a car, it's a death trap. But they're okay because they know the tornado's direction and it's moving away from them. And video like this, gotten back to a television station we can air live, will force people to do something about it. And that's one of the things that some of you might have an interest in doing this for us, is helping us stream live video back. It's a very risky proposition, and I don't recommend it unless you've been trained a good bit, if you've been to this thing several times. But the way all of our volunteers typically do, they have a phone or an iPad mini on the dash, and they just, now you can open up a Facebook live stream, and we can take that right on television. And when people see this, they do something. When people see radar, they see a bucket of spilled paint. But this is an EF4 tornado that's a long-track tornado. This would ultimately come through the western suburbs of Birmingham. This is the same tornado that came through places like Concord and Pratt City. And this was hard. I mentioned my father leaving when I was started 5th grade. We moved to Tuscaloosa, and there were some wonderful people here that loved us and encouraged us and helped us. 2 strange people in a strange land. And because of that, Tuscaloosa is a very special place for me. This tornado here killed 53 people. And this was hard stuff, guys. But again, this is my mission. This is what I do. This is what I want to do for the rest of my career. It's to try and help fix and repair the tornado warning. You play a crucial role in the warning process. Everybody in this room, you are now a trained spotter. You've just been through the basic class. When you come back after lunch, and I know you will, we're going to have the advanced class. And you walk out of here at 2 o'clock or 2:30 this afternoon, you are a trained spotter. You are now part of the weather enterprise. As Brian pointed out, the radar beam's up here. The radar beam goes in a straight line. The Earth what? Curves. Wait, Shaq said it doesn't curve. But he plays in the NBA. Later he said, well, I was just joking. But the only way we know what's going on down there is your eyes. And now you have the knowledge to give us the information we need, and reporting that, whether it's on the chat, on Slack, or whether it's social media, whatever. You play a vital, vital role in this whole thing. This is the debris ball on radar, the Tuscaloosa-Birmingham tornado crossing the county line. This is Tuscaloosa County. This is Jefferson. And again, what's so stinking sad, that's part of the city of Tuscaloosa in the air. And a lot of this would fall from the sky over Birmingham. It was horrifying if you were involved in that. Parts of people's lives, parts of their homes, furniture, small animals falling from the sky over Birmingham that were lofted 50 miles southwest of here. But again, that's the debris ball on radar. But you know what? We still don't exactly know what's going on down at the surface. We don't, because the radar beam is not hugging the ground. These 2 guys are heroes. These guys are heroes on that day, and I don't think they ever got the credit they deserve. This is from a couple of guys in rural Greene County in West Alabama. Now, they had a camera. They got off the dash, and they were shooting this thing. That's that large wedge tornado. That is the large wedge tornado that would hit Tuscaloosa and hit Birmingham. 40 minutes before it got into Tuscaloosa. And that video enabled a lot of things to happen. You saw me ratchet that up real quick when I saw that. Number one, all of a sudden now we have a tornado emergency for the cities of Tuscaloosa and Northport. If you know anybody that lives there, call them or text them now. Everything got serious here. We went from radar to this. And by the way, Brian and Coleman, they were up on another storm in Cordova at the same time. I didn't know what to do. There's no book, there's no manual on how to do this right. I had these guys in a tornado just that big in Walker County. So I was splitting it with these guys having the audio and this having the video. I didn't know what to do. You can't train for this. But I'm just saying, this is John Olshoe and Ben Greer. And they were doing it out of a servant's heart. They're not doing this for money or glory or anything else. And this is what we're looking for. We're looking for people with a servant's heart. And if you're here on a Saturday, on a nice day like today, I know that you have one. And this is why we need you. And again, I guarantee you there are people walking around today because of that live video right there from two guys. Now, Old Shoe used to work with me. He's a professional. Greer's a volunteer. John retired, and they just wanted to do this to help out. And goodness gracious, I can't tell you how many people said they saw that, and that's when they realized, yeah, this is really happening. So we have to have more people out in the field, more trained spotters. But this is why, I want to show you why you're going to do what you do. You're going to spend some time away from your family. You're going to spend some time doing things to help us that maybe you would be doing for yourself. Let me tell you why you're doing what you're doing here today. This is Danielle Downs. Let me just say, this is hard. She was 2 weeks away from graduating the University of Alabama. She was killed April 27, 2011. She wanted to be a social worker. She lost her life that day, as did Will Stevens. Will was a student at Stillman College in Tuscaloosa. He was a baseball player. Lauren Brown lost her life that day. Will, Lauren, and Danielle were together at 31 Beverly Heights, which is a house just east of DCH Regional Medical Center. And by the way, they did the right thing. In some cases, you hear the warning, you do the right thing, it's your day. Everybody in this room, we have a day appointed to be born, we have a day appointed that we die. And for some reason, it was their day. This is Miss Minnie Ackland. She was killed in Tuscaloosa that day. This is Angel Stillwell. This affected every socioeconomic group. I don't care. City, country, high income, low income, it crossed every line. She was from East Alabama. This is Haley and Mikey Kreider. They were kids at Concord Elementary. Goodness, I feel like I own some bricks in that school. I've been out there so many times. And they have a beautiful new school today. They lost their life April 27, 2011, as did Miss Bessie Brewster. Everybody said Miss Bessie had the best smile in Pratt City. She was killed April 27, 2011. Jonathan and Justin Doss, a couple of brothers from Cordova in Walker County, they died on that day. And again, this stuff is so hard for me. This is all I think about. Al and Angie Sanders lived in Shoal Creek Valley. They were home with their 3 daughters. The 3 daughters survived. These 2 parents were killed. They were taken that day. Why? I don't know. A lot of this, we won't have the answers until another place at another time. Carrie Lowe lost her life on April 27, 2011, leaving behind a husband and a newborn. Social media posts like this was one of her last ones. These things will haunt me for the rest of my life. I have a hard time looking at these faces. It's Ashley Harrison. She was 2 weeks away from graduating at the University of Alabama. She was from Dallas. Her boyfriend was Carson Tinker, the long snapper for the University of Alabama football team. She was lofted. Where her body was found is still a memorial today. Hopefully it stays there forever. But let me just say this. At the graduation, which was held later in the year, the graduation was postponed. This is Ashley's parents. The pain in Mrs. Harrison's eyes, if you can't see that, if you cannot feel her pain, that pain is visceral. If you can't see it or feel it, you're not alive. And this is what we've got to do. This is all I think about. We've got to go beyond what we're doing now to stop this suffering, to stop this insane loss of life. Can we stop it all? No, of course not. But we can do a whole better job of stopping the loss of life and preventing pain like this. I have 2 boys. We have 2 boys. My wife and I have been married for 36 years. I don't know. I have no idea what they feel like. No idea. Yeah, my father ran out on me. Well, so what? I've not had that kind of loss of life in my home, but this pain really affects me. I'm a different person because of what happened on that day. My focus has changed. If you want to learn more about that day, I encourage you to read this book. And I'm not in the book selling business. I have no financial interest in this, but I'm telling you, she got it right. Kim Cross, the lady that wrote this book. And I don't have time to read. I've not slept in a long time, but I listen to books when I drive from point A to point B. and that's how I do it. There's an audible.com version of this. You can read it. She got the science right. She got the passion right of the day. She got the stories right. If you want to learn more about me and the people in our office and him and the people that I talked about, some of those that lost their life, it's a riveting read. And let me just say, it is a very hard read, but it's a darn good one. And if you're into weather and if you're here today, everybody ought to read this book. Check it out at the library. She did an unbelievably good job with this. But let's move on and talk about where are we going here. And again, I promise I'll get you out on time. I get really wound up when I talk about this stuff because I'm so into it. We'll get you out right on time for the lunch break. But this is what I'm telling everybody in the weather enterprise. Everybody. The weather service, broadcasters, private sector, spotters, chasers, everybody, all of us. We've gotten to this point in society where we like to fight and feud with each other. We can't be successful fighting and feuding with everybody. We have to put egos and pride and power and titles and these territorial boundaries, these market boundaries aside to stop this insane loss of life. So that's the challenge I have for all of us, is to somehow check all this stuff. And what we need to do is to go into a padded room for about a week. I wish I could gather everybody in the weather enterprise to do that. We're going to go into a padded room for a week and knock out some of these problems. And some of it's really not that hard. So why did all these people die on that day, by the way? We've gone back to social science studies. We've learned a lot. And let me just say this. We've learned there are some people that don't take responsibility for anything. I can't help them. Sorry. There are some people that say, well, unless a government employee pulled me out of my house and stuck me in an underground government bunker, well, I got no warning. I can't help you. And I'm sorry, but that frees me to focus on the ones that want help, and that's most people. And that's been very freeing for me. But the number one reason people died, and I'm not going to go off on my tirade, but Brian's heard my tirade enough about this, is the siren mentality. I'm not here to do that today. You've heard me talk about this. I've said enough about this. This stuff is killing people. This technology is from World War I, and yet almost every Alabamian, the way they think they're going to get a tornado warning, it's that siren down the street. No, you're not going to hear one. Where did this come from? They've never been effective at reaching people inside a house. I mentioned the tornado in that gap in January of 2012, January 23rd. I don't need to look at Christina's picture. I feel like I know her. Christina Heichelbeck was a student at Shades Valley High School. Brilliant life in front of her, brilliant student, and she was killed that morning. The grieving parents, later that day, her father said the family didn't hear the what? Come on! I'm done with that. After this, I don't care if I make you mad. I'm sorry. And if there's any place in Alabama where maybe I fight with the people a little bit, it's this thing. And I was so mad after this. At the time, I had a 16-year-old son. The head of the weather service in Birmingham had a 16-year-old daughter. I wanted to go climb these poles, take those things down and burn them. And guess what? Then you know that you won't hear them. But that's not right. They serve a purpose. Sirens reach a limited number of people where? Outside. Outdoors. And if they can reach a few people that we can't reach any other way, fine. But we've got to educate people that this is not working. And by the way, I'm not throwing the parents under the bus. They want to stand here today begging you to stop, thinking you're going to hear some siren. We can't do this anymore. We cannot do this anymore. We got to move on. And, you know, we're starting to get we're finally starting to get people that are figuring this whole thing out. I think, Brian, part of the deal, people just, weather weenies, which we all are, we think they're kind of sexy. When those tornado sirens are saying, ooh, but this is cool, man. I mean, you know what I mean? It's kind of, but guys, it's not about us. There's some really, really good press going on here, and public officials are starting to get it. Do you spend $25 million on sirens, or do you get a weather radio for everybody in the county, properly programmed with a battery backup in it? You know what I'm going to say. And this, just between us girls, of course, there's 200,000 people watching down here. Weather radio is getting a little stale. Now, we don't say this publicly. We have been using storm-based warnings, polygons. By the way, what do? Respect the stinking polygon. This is not that hard. If you're in it, you do something, and if you're not, you don't. I think about 10 years we've had it here, and the problem is these are still county-based, not polygon-based. I don't know if that's ever going to change. But still, boy, they work well. They will wake you up. They will wake you up. And if a lot of people April 27th had one of those things, they'd be alive today. In the middle of the night, they'll wake you up. If you're not watching television, they will let you know there's something going on. You program them by counties, and that's still the baseline. Smartphone apps, I don't sell apps. I have no financial interest in anything I talk about today. None, zero. I don't like conflict of interest, but I do like this app. It's called Weather Radio by WDT, Weather Decision Technologies. That's the one I have on my phone. My wife has it. Our two boys have it. I know how the infrastructure is made. I know they're hard. It's a good company. They gave this thing away free after April 27th because a lot of people can't afford a $4 app. They gave it away free. That, to me, said their heart is in the right place. That's the one I like. There are other good ones. I can't comment on them because I don't use them, but that's the one I like, Weather Radio by WDT. We should also mention phones have wireless emergency alerts built in. Your phone has WIA built in. Anybody get an Amber Alert to freak you out here recently? Man, I was at the house one night. That thing went off. Whoop! And I'm thinking, I immediately thought there's a tornado warning, but there can't be. I'm not, what? And it was one of the Amber Alerts. But in theory, you get 3 types of alerts on your phone without doing anything. You don't have to buy an app. You don't have to do anything. By default, you should get Amber Alerts, flash flood warnings, tornado warnings. The truth is, though, I don't know how that sausage is made. It's a government thing, and not that I'm not going to say that. I want something I understand, and that's why I had my family use that Weather Radio app. But this seems to work. It seems to work pretty well. So, again, the more ways you have of getting a warning, the better off you are. And please don't turn those things off. And listen, I joke about the Amber Alerts. Hey, if I had a 10-year-old child missing, I would want to alert everybody in this state on your phone. I think it's a very valuable service, and I would ask you, please don't turn those things off. You can turn them off within the settings in your phone. I would recommend leaving WIA on, even if you got a good app. Lack of helmet use is a big reason people died April 27, 2011. Let's go back 19 years ago today. Anybody know what happened 19 years ago today? I know you do. We had an F5 tornado back then. It was an F5 back then. Now it's an EF5. F5 tornado came through the western suburbs of Birmingham. You probably have never heard of these places maybe. Oak Grove, Rock Creek, Sylvan Springs, McDonald Chapel, Pratt City, Edgewater. 32 people died in there, including Nathan Seals. 2 more died in St. Clair County from the same parent storm, a different tornado. The total death toll was 34. Nathan was 8 years old. He lived in Rock Creek. And I'd say this funeral was probably the hardest one maybe I've ever seen. And I've seen a lot of them. And let me just say, that's what motivates me. There have been too many funerals on my watch going back to the late 70s. We've got to stop this. Family of 5, they were lofted. And hear me now, they did the right thing. They heard the warning, and they did everything that they were supposed to do. At the time, they did everything we thought you're supposed to do. They missed one thing. The family of 5 was lofted. And by the way, during a strong, violent tornado, if you're directly in the path, you will be lofted. Most people lose their life to wounds to the skull region while you're aloft. They landed a long way away from their house. They were out there in the rain in this horrific situation for hours before the first responders could even find them. This is Nathan's casket. This is the father, Matthew Seals. He had a severe back injury. He'll never walk again. He's in a wheelchair unless there's some type of miracle. This was the mom. She had a punctured lung and 2 broken legs, I believe, and the siblings were beat to a pulp, but they all survived. I'm pretty close friends with Matthew. Matthew's been with us here at our events over the years. He likes to talk about this day and share his knowledge and share his passion for this helmet issue. But the bottom line is the research shows that if Nathan would have had a helmet on, he'd be alive today and he'd be just fine. He'd be in his 20s. Everybody in your safe place, you got to have a helmet. That's what we missed. And on April 27, 2011, a lot of those that died, if they would have had a helmet on, they'd be alive today. And yeah, it looks stupid. Well, so what? A lot of older people won't say, well, it looks stupid. Well, my question to you is every human life precious? And the answer is yes. Yeah, it looks cool for a 7-year-old kid to put on a batting helmet or a bicycle helmet, but it looks kind of stupid for some old guy like me. I don't care. You put it on. Everybody should have 2 things that we learned on this deal. 2 things we learned from this day. Number 1, you should have a helmet for everybody. And number 2, in your pocket, you need a portable air horn. Those things you can buy at Walmart, Target, they're not that expensive because they were out there in the rain for 4 hours and nobody could find them. If you had an air horn, you could squeeze that sucker, and the first responders have been trained to listen for that. And people say, well, why don't you use a whistle? Well, if you're injured severely like they were, you cannot force air through a whistle, but you can probably squeeze that air horn. And by having one in your pocket, that increases your chances of getting help a lot sooner instead of having to wait out there for hours and hours. So helmet use is a big deal, and we got to work on that. This is our fault. This is on our back all the way. False alarms. False alarms. If you hear a warning over and over and over and over and over and nothing happens, it's the cry wolf syndrome. And we heard this a lot in the verbatims coming back in the research. I hear warnings all the time and nothing ever happens. The false alarm ratio in 2011 here was 83. 83% of tornado warnings were false. I don't blame people. That's on our back. But let me just say this. By going back to basic science and picking up some new knowledge, that sucker is down to 20. I never thought in my lifetime the FAR would be 20 here, but it is, which means tornado warnings mean business if you hear one today. We have a better understanding of these squall line tornadoes. The QLC, who came up with quasi-linear convective system? When I grew up, it was a squall line. Whatever. Many of our tornadoes occur in lines. They're very small. They don't last long. They're very challenging. It is like playing whack-a-mole when it comes to warning for these suckers. I don't even think we're good enough to do it, but we have a better understanding of these things. We've learned that high-base storms don't do tornadoes, kind of like Wednesday. I think that had something to do with the lack of tornadoes Wednesday, was the fact that the LCLs, lifted condensation levels, were over 1,000 meters, or they were near 1,000 meters that day. So the Weather Service just stopped issuing warnings for high-base storms. And boy, that's made a huge difference. We now have dual polarization radar. Now we have that magical product. Well, all of them are magical. But the product we use to see tornado debris is called what? Any radar weenies in the room? CC. You got it. CC, correlation coefficient. The radar can correlate the echoes in a bin, and if it sees something that doesn't correlate very well, it's not rain, it's not precipitation, it's not a hydrometeor, it's biological or it's debris or something else. And by seeing a negative CC hole in radar, and you can see this on radar scope if you've got that on your phone, then we know there's a good chance debris is being lofted. And boy, that's a great product that really helps us. And finally, it's you. You've made the difference. We have better communication. We have highly trained spotters. We have more of you, and after this, we'll have more than we had yesterday. And that's made a big difference as well. Your input is critical, critical. Here's the deal. Everybody thinks, well, I'm going to get in this storm spotting business so I can help the Weather Service warn for tornadoes. Warn and warn and warn. Hey, a lot of times you're going to help the Weather Service not warn. It's going to keep their finger off the button because you're going to say, I've got a wall cloud, but there is nothing underneath it. There is no funnel cloud. There is no tornado. And that'll keep that finger off that button a lot of times. So I can't tell you how important your job is in this whole process. And this has gotten out of hand. Inconsistent messaging. Maybe I'm just a simpleton. When I was an old boy, I lived in Greenville, Alabama. You never heard of that, have you? You have not. If you ever drive to Gulf Shores, you go through Greenville on I-65. If you ever get a speeding ticket in Greenville, call me. My best friend from first grade is the mayor. I'm not kidding. His name is Dexter McClendon. He's a great guy. I'm just an old country boy from Butler County. I moved to Tuscaloosa when I started fifth grade, but I'm from Butler County. And maybe I just get confused easily, but I guarantee I understand the culture of this state, and people are starting to get confused. Anybody know what this is? If you don't, I would hope that you would learn this. This is the daily risk defined by the Storm Prediction Center. We've had way too many of these lately. We've had a lot of these maps out here lately, but every day, meteorologists at the Storm Prediction Center, and I think they're brilliant people. Some of my heroes work there. Guys like John Hart, Rich Thompson, they're brilliant. They're like our Army Rangers, our Navy SEALs. They produce this product every day, and it really goes out to 7 days. And you're going to fall, if you're going to have storms, you're going to fall in one of these categories. Over here, thunderstorms not severe. Number one is a marginal. That is the lowest in risk, marginal risk. Number two, slight. I don't like that word. Nobody likes that word. When people hear slight, they think it means nothing's going to happen. But the truth is, most tornadoes and severe storms occur on slight risk days. This is where most of them happen right here. But most days you get marginal and slight. Enhanced is Category 3. Moderate is Category 4. This doesn't happen a lot. We had a moderate risk on Wednesday, and this is high. You might see 3 or 4 or 5 a day or a year, and that's it. 3 or 4 or 5 a year nationally. We've had 3 this year. We had one Wednesday over South Georgia and South Carolina. There's been a lot of debate in the weather community about have they been issuing too many high risks this year. I don't want to play that game. But I'd like to think that you would memorize this. I have poured out my heart and my soul trying to get people to learn these categories, because you need to know how they work. You need to know what they mean, because we're going to show you these maps on TV, and we're going to talk about them, and that's the deal. And this was the outlook the day before April 27, 2011. Hey, you could not draw that any better if you knew what was going to happen. This is unbelievably good. I mean, you could give me a map of the tornado touchdowns and the severe weather reports the next day. I couldn't draw a map that good, even knowing what was going to happen. That's why these guys are darn good at what they do. Now, we've still got a little inconsistency stuff going on here, but let me tell you what, we're moving. We're getting in the right direction on this real quick. I get messages like this all the time on the Facebag and the Tweeter. I mean, I get Tweeter, Facebag messages all day. Snapchat, Instagram, I get them all day, and I try and answer all of them. But this one came in, this was Tuesday morning, this past Tuesday morning, the day before Wednesday. Tuesday's always the day before Wednesday, isn't it? Yeah. Like I say, I'm from Butler County. I'm sorry. I was looking at the National Weather Service Birmingham graphic and noticed that it had a larger area in the moderate risk than other graphics I've seen. My question, which is the most accurate as of right now? Because the guys at the Storm Prediction Center, their product looked like this. Do you see any difference in this and this? The moderate risk over here is pulled up to Birmingham, and on this one, the moderate risk stops at about Rockford and Prattville. And this is the inconsistency we're trying to fix. And listen, I am not going to play a game here of trying to tell you, is the Weather Service in Birmingham and the Storm Prediction Center better? They are brilliant. Kevin Laws, the Science Operations Officer at Birmingham, he's the best. The staff down there is brilliant. Storm Prediction Center guys, Hart, Thompson, this team, brilliant. What we've got to do is just learn to communicate a little better and maybe change our culture. I think the guys at the SPC, they don't know how much of a rock star they are. Their products are widely distributed. For years, this was kind of internal, and now the world sees it. But trust me, great work is being done to get these maps the same and coordinated. Collaboration done before these products are issued. Great things are happening here. That's one good thing that's come out of all of this. But this is my concern. I have great concern that the watch warning system is going to collapse if we don't do something. And I don't want it to. Does it need improving? Yes. So now what's happening? You've got all these new firms issuing their own warnings, independent of the Weather Service. Now, let's be fair, Brian. These guys don't call them warnings. They call them alerts. And if you've listened to our show, Weather Brains, we had one of these guys on. We gave him a hard time, but you know what? I see Mrs. Harrison's eyes. I see the pain in her eyes. That's all I see. And if I make somebody mad, I don't care. But they're issuing their own warnings. They're claiming a probability of detection of 95% plus and a false alarm ratio of what? 5. I said, well, let's see your documentation. And we're still waiting on that. No, we're not that good. And they're selling this directly to the public, and this is their thing. And look, I don't care if they bash us. That's fine. I don't care. Fine. Don't wait on me. Find out from Metloop. But here's the problem: local television stations are now issuing their own warnings. Let's go to Dallas-Fort Worth. The TV warning is this blue one right here. The Weather Service warning is the red one. 2 polygons. So let's say you live, this is out to the west of Fort Worth. Let's say you live right here. Who you going to believe? If you believe the TV guys, I got no danger, I'm good. But if you believe the Weather Service, you are in danger. What do? This will introduce mass confusion. If every TV station issues their own warnings, it is absolute chaos. insane chaos that will lead to inaction. I've got social science studies that will prove that, and it's going to kill people. And yet all these TV stations starting to go their own way, and these private businesses are putting out these apps. Get the MetLoop app, you get your own warnings, we're better, and don't believe the Weather Service because we're independent and we're better than they are. I feel sorry for this guy. I mean, Weather Brain's 580, by the way, if you want to go back and watch or listen. And look, I'm sure he's a nice guy, but he didn't know what he was going to get into. I bet you I'm the only guy here old enough to remember this movie, except for him. Cool Hand Luke. What we have here is a failure to communicate. And this is where we're going here. And they're not going to listen. This is people. And again, we're weather dweebs in here. I'm talking Joe Q public that go to the Dollar Generals and the Walmarts. That's what I tell people in the weather enterprise. We need to go hang out in a Dollar General and talk with real people and see what they really think about our products and services. And this is the look they're giving us now because of this confusion problem. We need one source for warnings and these outlooks. Now, in my opinion, it should be the Weather Service. These guys are good. We standardize on it. Now listen, we will communicate it differently. I will communicate it differently than him. And the guys on the other channels will communicate it differently than me. But the message has to be the same. You choose the source that you like, but the message has to be unified and consistent when it comes to warnings and call to action statements. Now, and let me just say this. We do have work to do. Brian, you seen this one? I don't know if anybody took chemistry. We call this the periodic table of Weather Service watches, warnings, and advisories. We think we have a few too many, and the colors are a little confusing. I don't even know what half this stuff means, and I've been doing this for 40 years. So we've clearly got work to do. To understand, I believe we have work to do within our enterprise, within the current system. Yes, it needs to be adjusted. Do we need to repair it or revamp it? By revamp it, that's a nuke and pave. Or do we just kind of make some tweaks and adjustments? I'm probably in favor of a repair, but there's work underway right now to see what we need to do with this based on social science. Here's a prototype coming from this HasSimp workshop. There's one idea of replacing all three of these with one word, replacing emergency, warning, and advisory with just the word warning, but with these impact colors and levels, purple, red, and yellow. And again, this is not going to happen. This is just an idea. And watch and outlook are going to be replaced by the word potential in this model, with higher risk and lower risk. And this is a way to simplify things. And again, it doesn't matter what I think. It matters what you think. And people in the Walmarts and the Targets in the real world think. And we're working on that now. And I'm so tired of talking about this. That's the one thing. I think I'm going to stop talking. I have been all over talking about this. We need to roll up our sleeves and do something. And we're going to try and do something this summer. We're going to get a bunch of people together in Kansas City and do something. Instead of talking, we need some action here. So we are talking. A lot of things are happening. This is a webinar from the National Weather Association. Should weather messaging wear uniforms? These are very good discussions going on now. I'm involved in this organization, and again, some good work's going to happen here. So, but what I recommend we start with are some simple things like consistent watches and warnings. If anybody, and I know some my TV friends are going to be watching this down here online, I'm begging you not to issue your own warnings. I'm really begging you. Please don't. Because if you do it and your friends do it at the other channel, nobody's going to listen to any of us. Nobody. We have to be consistent. And we have to have consistent watches and warnings. All these external products. And again, if a private company has a private business where they're consulting them, that's okay. But I'm talking to the public. We can't be in this business. Consistent call to action messages. This is going to drive me nuts. In some places, you turn on the TV, one TV guy says if a tornado's coming, the only way you'll survive is to be underground. You turn on the next channel, he says, get in your car and drive. You turn on the next channel, and he says, go to a small room on the lowest floor. What are you supposed to do? It's insane. We have to have at least a consistent call to action message. Can we agree upon this? It is like a bunch of first graders. We need to get in the room and just decide we're going to say the same thing. Use the same colors. Hello, friends. Let's use the same crayons. But I just wanted to share this with you. This is the problem where we're going down a bad path. And if we don't stop this business where everybody's doing their own warnings and watches and all these weather emergency days. There's some TV stations, every day is 4 out of 5 days, a weather emergency day or weather whatever it is day. You know, this hyperbole and all this stuff's got to stop. But mainly I wanted to thank you for being here today, for your heart. And what we have to learn in this business is humility. If you don't have humility in my business, you'll learn it real fast. There's a lot of things we don't know. There's a lot of things we can't do. Anybody remember the Snowmageddon 3 years ago? That's a dose of humility right there. I said this forecast Wednesday was a darn good forecast. The forecast 3 years ago for that event was a darn bad forecast. I apologize for it. I'm a straight shooter. One thing about me, you can fault me for a lot of different things. I'm a straight shooter. So you will learn that. But everybody here, you've got a good heart, and thank you for having that heart. So real quick, I want to chase one more rabbit, and we'll take a break for lunch. These people, just off the record, between us and our 200,000 people down here, these Facebook Lives really creep me out. I mean, it's just like way too many people watch this. And I do think we have to learn to get along with the news people better. This is their meme. It's just like, so this is NBC Nightly News this year. We had a tornado that came through Pickens County, Alabama. I bet y'all never been to Aliceville, have you? Maybe, okay. Saps is a suburb of Aliceville. That tornado could have killed 50 people. The people heard the warning. They got into a community tornado shelter that they had. The system worked flawlessly, and nobody died. Horrible damage, and it was bad. But and we were so happy that the way it worked, and then that night at 5:30, these guys come on. What's the first word out of their mouths? Tornado strikes Alabama without warning. That's not true. They just made this up. You talk about fake news. We've been dealing with this stuff for years and years and years, and it's not just these guys. And by the way, this is the tornado warning polygon for that storm that could have killed 50 people. What's the matter with these guys? I mean, you know, we try and get them on this weather brains, and they won't even come on now. This was an unbelievably good warning. Aliceville is here. The tornado came through right here, right square in the middle of the polygon. The supercell storm is right here. Warning couldn't have been any better. I cut off Grey's Anatomy. I had people threatening to cut my thing off. I mean, it was horrible. Can I say that on here? Yeah. So, oh, brother, I took your show right down the tubes, didn't I? Yeah. See, I see the stuff, and I can't say it, but trust me, you cut off Grey's Anatomy, you're going to get it. But it worked really well, and so here is, and people say, well, why do you have a problem in saying that? Well, number one, it's a flat-out lie. And number two, it discredits the system. Well, if there was no warning for this storm, I guess they just can't warn for any of these storms. I'm not going to pay attention to the warnings. It discredits the system. It discredits everybody within the weather enterprise. Weather service, media, private sector, people in emergency management. And this isn't the first time. This is one of their memes, okay? So here we go with her. And you know, and again, these are nice people. They don't know anything about tornadoes. They live in New York City. They don't know anything about this stuff. But they should have researchers, and they ought to be fact-checking the stuff. Look, I would hate to read that prompter. I am not a reader guy. I'd get up there and talk. But this was after Christina Heichelbeck was killed on January 23rd, 2012. I've been up all night. This was a pre-dawn 4 a.m. tornado. And we had one other death in Oak Grove. We had 2 people killed that morning. And I hadn't slept one second that day. And we have a little bitty break at 5:30. The news just never stops now when this stuff comes on. I just happened to walk in my little closet, and the first words out of her mouth, rare tornado strikes Alabama. What are the next 2 words? Without warning. What do you mean? There was a warning 32 minutes before it hit Clay. She just made that up. And, you know, here's my social media rule. Count to 10. Trust me. If you saw the stuff I see, you got to learn how to count to 10. I didn't. And it wasn't bad. I just said, Diane, you just said there was no warning. I say there was. I've got proof. You come on my show, or I'll come on your show, and let's debate. The next day, it got into a full-blown Twitter stink. I mean, I don't know who makes these memes. It's just like... I have no idea. And you know what? She's a nice lady. She doesn't know anything. She knows nothing about tornadoes. She didn't know. I don't know if she just made it up or ad-libbed it or what, but you can't be doing that. It discredits the system. And I think what we have to do is to reach out in a non-confrontational way and educate them as to how this whole thing works. You know more about this business than they do on the national level, and we've just got to work on that. And we're down to this thing where this, now this is their new meme. Every time here, Brian, 11 twisters touchdown. Now these were in rural Georgia, okay? Rural Georgia, but yet millions were in the path. That's not true. There were millions in the path of 11 tornadoes in rural South Georgia. There may be 25,000. But it's like this stuff has just got to stop, and I don't know what to do about it sometimes. But anyway, a few things, and we'll break for lunch. I'm way past. But we're working hard in the weather enterprise to fix this stuff we're talking about, working very hard to come up with a consistent, unified message. But what you do is crucial. So when you get on that Slack chat with us, when you give reports to us, and you provide us a live stream, and I do want to talk about live streaming before we leave at the end of the next session. We're going to do an advanced session at 1, and then we're out of here. I want to talk about live streaming, but if you do that, I just wanted to thank you because you will help me so much. I can't tell you how crucial it is. And one more thing, we've learned that is blowing me away. People can't find their house on a map. I will post a really easy-to-read map on Facebook and a very clear explanation. And what's the first questions I get? What about Jasper? What about Cullman? What about East Aboga? What about Aniana? What about Anniston? What about Talladega? What about Rockford? What about Brent? What about Centerville? What about Marion? What about Demopolis? What about Carrollton? What about Fayette? What about why are people asking that? They can't find their house on a map. And this is a universal problem. This is not just an Alabama problem. This is a universal problem. And we've got to look at how we message people before severe weather events. Now, during the event, I'll call out the barbecue joint in the barn. I'm good at that. I understand that. But before an event, we have to use maps. And the research we're starting to see, what percentage of people here do you think can't find their house on a map within 50 miles, putting a blue dot on a blank map with counties and state lines? About 80%. 80%. Geography literacy is a problem. And of course, literacy period's a problem. Some people don't have good reading skills. But all of this is being under consideration. We are working hard. This is my passion right now, is to try and help correct the warning process problems. But I promise, in the weather enterprise, we're working hard. But thank you all for being here today. And again, the good stuff, it's going to start at 1. You got 1 hour. Brian, you come on up. I don't know. There are places to eat at the Sheridan. There are places to eat around here. So, there are plenty of opportunities. So you got an hour break. We'll be back at 1 o'clock for one last session, and you are done for the day. Thank you all for being here today. We'll see you back at 1 o'clock sharp. 1 o'clock sharp. Thank you guys for watching on the stream. And we're going to turn this off because this session has officially ended.